super excited to start the very first lesson on big data. And thank you again for choosing this course. I promise we're going to learn a lot about Hadoop and big data. Ready? Let's get started. In this lesson, we're going to see what is big data and some examples of big data first. Then we'll see what are the problems that come with big data. We will then talk about what Hadoop can offer in terms of solutions to big data problems. And finally, we'll compare traditional solutions with Hadoop. Okay? If you ask me, tell me in one sentence what is big data? I would say big data is extremely huge volume of data. To that answer, the follow-up question you can ask is what is considered huge? 10 GB, 100 GB, or 100 terabyte? What is huge? There is no straight hard number that defines huge or big data. I know this is not the answer you're looking for. I can see your disappointment. There are two reasons why there is no straightforward answer to this question. First, what is considered big or huge today in terms of data size or volume need not be considered as big a year from now. It is very much a moving target. Second, it's all relative. What you and I consider to be big may not be the case for companies like Google and Facebook. Hence, for those two reasons, it's very hard to put a number to define big data volume. Let's say if we are defining big data problem in terms of pure volume alone, then in our opinion, when you say 100 GB, I would say not a chance. It is not big data. We all have hard disk greater than 100 GB. So it's clearly not big data. How about 1 terabyte? Still no. Because a well-defined traditional database can handle 1 terabyte or even more without any issues. But what about 100 terabytes? Likely, some would claim 100 terabytes to be a big data problem and others might disagree. Again, it's all relative. What about 1000 terabyte? Now we are talking in scales of petabytes. I would say it's definitely big data. You have to understand volume of data is not the only factor to classify your data to be big data or not. So what are the factors should be considered? Let's say we work at a startup and we recently launched a very successful email service where users can log in to send and receive emails. Our email service is so good, let's say it's even better than Gmail. In 3 months, we have 100,000 active users signed up and using our service. Hypothetically, let's say we are currently using a traditional database to store email messages and its attachments. Also, our current size of the database is 1 terabyte. So, do we have a big data problem? The simple, straightforward answer is no, because 1 terabyte is not that huge to classify it as a big data problem. The more important question is, at this growth rate, will we have a big data problem in the near future? To answer that, we need to consider 3 factors. The first one is volume. It's an obvious factor, right? In 3 months, our startup has 100,000 active users and our volume is 1 terabyte. If we have positive growth at the same rate, at the end of the year, we will have 400,000 users and our volume will be 4 terabyte. End of year 2, with the same growth rate, we'll have 8 terabytes. What if we doubled or tripled our user base every 3 months? So the bottom line is, we should not just look at the volume when we think of big data. We should also look at the rate in which our data grows. In other words, we should watch the velocity or speed of our data growth. Velocity. This is the next important factor to consider. Velocity tells you how fast your data is growing. If your data volume stays at 1 terabyte for a year, all you need is a good database. But if your growth rate is 1 terabyte every week, then you have to think about a scalable big data solution. Most of the time, volume and velocity is all you need to decide whether you have a big data problem or not. The next factor to consider is variety. Variety adds one more dimension. Our data in traditional databases are highly structured, that is rows and columns. But take, for instance, our hypothetical startup email service. It receives data in various formats, right? Text for the actual messages, images and videos as attachments. When you have data coming into our system in different formats and you have to process or analyze the data in different formats, traditional database systems are sure to fail. And when combined with high volume and velocity, you for sure have a big data problem. So whenever you're asking yourself whether I have a big data problem or not, take these three V's, volume, velocity, and variety, into consideration. This will guide you in understanding whether the problem you're facing now is a big data problem or not. This happens to big data consultants all the time. They will be called in by clients with data storage or performance issues and hope that a big data solution like Hadoop is going to solve their problem. And most of the time, their answers will fail in the volume and velocity tests. The volume will be in the higher gigabytes or low terabytes, and their growth rate is relatively low for the past 6 months and in the foreseeable future. Hence, their volume does not qualify as big data. And also, their data growth will be very low and it fails the velocity test as well. What the client needs is to optimize the existing process and not a sophisticated big data solution. Now you know what is big data. And given a scenario, if someone comes up to you and asks whether their data problems can be solved by big data solutions, you know what are the factors to consider to make a sound decision. Volume, velocity, and variety. The three V's. Okay, so when we say big data, we are potentially talking about hundreds to thousands of terabytes. If you are new to big data space, you're probably wondering, is there really a use case? The answer is absolutely yes across all domains. You take any domain and you can see big data problems. Let's talk about science first. The Large Hadron Collider at CERN produces about 1 petabyte of data every second. That is right, 1 petabyte every second. Mostly sensor data from their equipments. Their volume is so huge they don't even retain or store all the data they produce. NASA gathers about 1.73 gigabytes of data every hour about weather, geolocation data from their satellites, etc. Let's talk about the government. NSA, that is National Security Agency, is known for its controversial data collection programs. And guess how much NSA's data center at Utah can house in terms of volume? A yottabyte of data. That is 1 trillion terabytes of data. Pretty massive, isn't it? In March 2012, Obama's administration announced about $200 million in big data initiatives. So you can understand the significance behind big data and its analysis. Even though we cannot technically classify the next one under government, it's an interesting use case, so I included it anyway. Obama's second term election campaign used big data analytics, which gave them a competitive edge to actually win the election. That's pretty powerful, isn't it? Next, let's talk about the private sector. With the advent of social media like Facebook, Twitter, LinkedIn, etc., there is no scarcity of data. eBay is known to have a 40 petabyte cluster and Facebook a 30 petabyte cluster. These numbers are probably much more now since the stats are a little old. Big data is not only produced and analyzed in social media companies, but also in retail space. It is most common in several major retail websites to capture clickstream data. For example, let's say you shop at Amazon.com. Amazon is not only capturing data when you click checkout. Your every click on their website is tracked to bring a personalized shopping experience. When Amazon shows you recommendations, big data analytics is at work behind the scenes. I've included the sources for all the information I provided in this slide in the lesson notes. Now you should be convinced that big data exists, even if you did not believe it before. So, we have big data. So what? Big data comes with big problems. Let's talk about few problems you may run into. Since the data sets are huge, you need to find a way to store them as efficient as possible. I'm not just talking about efficiency in terms of storage space, but also efficiency in storing the dataset that is suitable for computation. Another problem you should worry about when you deal with big data set is about data loss due to corruption in data or due to hardware failure. And you need to have proper recovery strategies in place. The main purpose of storing data is to analyze them, right? How much time does it take to analyze and provide a solution to a problem using your big data is $1 million question. What's good in storing the data when you cannot analyze or process the data in reasonable time? With big data sets, computation with reasonable execution times is a challenge. Finally, the cost and the most important challenge. You're going to need a lot of storage space and a lot of computational power. So your solution that you plan to use should be cost effective. But what is the need for new big data solution like Hadoop? Why traditional database solutions like MySQL or Oracle is not a good solution? With traditional RDBMS, you will see scalability issues when you start moving up in data volume in terms of terabytes. You'll be forced to denormalize and pre-aggregate the data for faster query execution time. And as the data gets bigger, you'll be forced to make changes to the process in terms of changing the indexes, optimizing the queries, etc. If you worked with databases before, this will sound very familiar to you. Assuming your database is running with enough hardware resources, when you see a performance issue, still you have to make changes to the query itself or the way in which your data is accessed. There is no working around it. You cannot add more hardware resources or more computer nodes and distribute the problem to bring the computation time down. Meaning to say, database is not horizontally scalable. You cannot add more resources or more computation nodes and hope the execution time or the performance will improve. The second problem is databases are designed to process structured data. That is, when your data does not have a proper structure, in that case, a database will struggle. Furthermore, a database is not a good choice when you have variety of data. That is, data in several formats like text, images, videos, etc. Other challenge is a good enterprise-grade database solution can be quite expensive for relatively low volume of data. When you add hardware costs and platinum-grade storage costs, it's going to be quite expensive. Next, distributed computation solutions like grid computing are essentially many nodes operating on data parallelly and hence does faster computation. But there are two challenges though. The first one is grid or high performance computing is good for compute intensive tasks with relatively low volume of data, but does not perform well when the data volume is huge. The second problem is grid computing requires a good experience with low level programming to implement, and hence it is not suitable for mainstream. So a good solution should, of course, handle huge volume of data. It should provide efficient storage, that is, ability to store data efficiently. Data loss is unavoidable. So the proposed solution should implement good recovery strategies. And the solution should be horizontally scalable as your data grows. Most importantly, it should be cost effective. And finally, minimize the learning curve. It should be easy for programmers and data analysts and non-programmers to work with the framework or the system. This is exactly what Hadoop offers. It can handle huge volume of data. It can store data efficiently in terms of both storage and computation. It has good recovery solution for data loss in place. It can horizontally scale, and that is very important. So as your data gets bigger, you can add more nodes and everything will work seamlessly. It's that simple. It is cost effective, meaning we don't need any specialized hardware to run Hadoop. And hence, it's great even for startups. Finally, it's easy to learn and implement. So, is Hadoop a replacement for database? The straight answer is no. There are things Hadoop is good at, and there are things that database is good at. Look at this slide. RDBMS work exceptionally well with volume in low terabytes, whereas with Hadoop, The volume we speak is in terms of petabytes. Hadoop can work with dynamic schema and can support files with many different formats, whereas in database, the schema is very strict and not so flexible and cannot handle multiple formats. Next important distinction is scaling. Database solutions can scale vertically, meaning you can add more resources to the existing solution. And to make any improvements, you have to improve the process itself, like tuning the queries, adding more indexes, etc. But it will not scale horizontally. That is, you cannot bring down the execution time or you cannot improve performance of a query by simply adding more computers. That is, you cannot distribute the problem into many nodes. Finally, the cost. Your database solution can get expensive very quickly when you increase the volume of data you're trying to process. Whereas Hadoop offers a cost-effective solution. Hadoop infrastructure is made up of commodity computers, meaning there is no need for specialized hardware. Commodity computers doesn't mean cheap computers. It is still enterprise-grade hardware, but relatively inexpensive as opposed to specialized equipment. It is important to know Hadoop is a batch processing system. It is not as interactive as a database. You cannot expect millisecond response times with Hadoop as you would expect in a database. With Hadoop, you write the file or dataset once and operate or analyze the data multiple times. Whereas with the database, you can read and write multiple times. But the gaps between Hadoop and RDBMS are closing in. Hadoop offers a cost-effective solution to big data problems. But Hadoop is not the only solution that is available in the market now. NoSQL databases like HBase and Cassandra bring a great deal of value in analyzing huge volume of data. And it's a great alternative for RDBMS. When I say huge volume of data, we are talking millions of columns. That's right, millions of columns and billions of rows. At this point, you should have a good idea of what is classified big data and what are the challenges with it. We also saw some of the offerings of Hadoop in comparison with traditional systems. In the Understanding Big Data Problem lesson, we'll dive deeper into how Hadoop actually proposed solutions to the big data problems that we discussed in this lesson. With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. Now you know the key characteristics of big data. It is now time to understand the challenges or problems that come with big data sets. So in this lesson, let's take a sample big data problem, analyze it, and see how we can arrive at a solution together. Ready? Imagine you work at one of the major exchanges like New York Stock Exchange or NASDAQ. One morning, someone from your risk department stops by your desk and asks you to calculate the maximum closing price of every stock symbol that is ever traded in the exchange since inception. Also assume the size of the dataset you are given is 1 terabyte. So your dataset would look like this. So each line in this dataset is an information about a stock for a given date. Immediately, the business user who gave this problem asks you for an ETA on when he can expect the results. Wow, there is a lot to think here. So you ask him to give you some time and you start to work. What would be your next steps? You have two things to figure out. The first one is storage and second one is computation. Let's talk about storage first. So your workstation has only 20 GB of free space, but the size of the data set is 1 terabyte. So you go to your storage team and ask them to copy the data set to a NAS server or even a SAN server. NAS stands for Network Attached Storage and SAN stands for Storage Area Network. So once the dataset is copied, you ask them to give you the location of the dataset. So a NAS or a SAN is connected to your network, so any computer with access to the network can access the data, providing if they have permission to see the data. So far good. The data is stored and you have access to the data. Now you set out to solve the next problem, which is computation. You're a Java programmer, so you wrote an optimized Java program to parse the data set and perform the computation. Everything looks good, and you're now ready to execute the program against the data set. You realize it's already noon. The business user who gave you this request stopped by for an ETA. That's an interesting question, isn't it? So you start to think, what is the ETA for this whole operation to complete? And you come up with the result set. For the program to work on the dataset, first the dataset needs to be copied from the storage to the working memory or RAM. So how long does it take to copy a 1 terabyte dataset from storage? Let's take our traditional hard disk drive. That is the one that is connected to a laptop or workstation, etc., right? HDDs, or hard disk drive, have magnetic platters in which the data is stored. When you request to read data, the head in the hard disk first positions itself on the platter and start transferring the data from the platter to the head. The speed in which the data is transferred from the platter to the head is called the data access rate. This is very important, so listen carefully, right? Average data access rates in HDDs is usually about 122 megabytes per second. So if you do the math, to read a 1 terabyte file from a hard disk drive, you need 2 hours and 22 minutes. Wow. Now that is for a HDD that is connected to your workstation. When you transfer a file from a NAS server or from your SAN even, right? You should know the transfer rate of the hard disk drives in the NAS servers. For now, we will assume it is same as the regular HDD, which is 122 megabytes per second. And hence it would take 2 hours and 22 minutes. Now what about the computation time? Since you have not executed the program yet, at least once, you cannot say for sure. Plus, your data comes from a storage server that is attached to the network. So you have to consider the network bandwidth also. So with all that in mind, you give him an ETA of about 3 hours. But it could be easily over 3 hours since you're not sure about the computation time. Your business user is so shocked to hear 3 hours for an ETA. So he asks the next question. Can we get it sooner than 3 hours? Say maybe in 30 minutes? You know there is no way you can execute the results in 30 minutes. Of course, the business cannot wait for 3 hours, especially in finance where time is money, right? So let's work this problem together. How can we calculate the result in less than 30 minutes? Let's break this down. Majority of the time you spend in calculating the result set will be attributed to 2 tasks. First is transferring the data from storage or hard disk drive, which is about 2.5 hours. And the second task is the computation time, right? That is the time to perform the actual calculation by your program. Let's say it's going to take about 60 minutes. It could be more or it could be less. I have a crazy idea. What if we replace HDD by SSD? SSD stands for solid state drives. SSDs are very powerful alternative for HDD. SSD does not have magnetic platters or heads. They do not have any moving components and it's based on flash memory. So it is extremely fast. Sounds great. So why don't we use SSD in place of HDD? By doing that, we can significantly reduce the time it would take to read the data from the storage. But here's the problem. SSD comes with a price. They're usually 5 to 6 times in price than your regular HDD. Although the price continues to go down, given the data volume that we are talking about with respect to big data, it is not a viable option right now. So for now, we are stuck with hard disk drives. Let's talk about how we can reduce the computation time. Hypothetically, we think the program will take 60 minutes to complete. Also assume your program is already optimized for execution. So what can be done next? Any ideas? I have a crazy idea. How about dividing the 1 terabyte data set into 100 equal sized chunks or blocks and have 100 computers or 100 nodes do the computation parallelly? In theory, this means you cut the data access rate by a factor of 100 and also the computation time by a factor of 100. So with this idea, you can bring the data access time to less than 2 minutes and computation time in less than 1 minute. So that sounds great. It is a promising idea, so let's explore even further. There are a couple of issues here. If you have more than one chunk of your data set stored in the same hard drive, you cannot get a true parallel read because there is only one head in your hard disk which does the actual read. But for the sake of the argument, let's assume you get a true parallel read, which means you have 100 nodes trying to read data at the same time. Now, assuming the data can be read parallelly, you will now have 100 times 122 megabytes per second of data flowing through the network. Imagine this. What would happen when each one of your family member at home starts to stream their favorite TV show or movie at the same time using a single internet connection at your home? It would result in a very poor streaming experience with a lot of buffering. No one in the family can enjoy their show, right? What you have essentially done is choked up your network. The download speed requested by each one of the devices combinedly exceeded the download speed offered by the internet connection, resulting in a poor service. This is exactly what will happen here when 100 nodes try to transfer the data over the network at the same time. So how can we solve this? Why do we have to rely on a storage which is attached to the network? Why don't we bring the data closer to the computation? That is, why don't we store the data locally in each node's hard disk? So you would store block 1 of data in node 1, block 2 of data in node 2, etc. Something like this. Now we can achieve a true parallel read on all 100 nodes. And also we have eliminated the network bandwidth issue. Perfect. That's a significant improvement to our design, right? Now let's talk about something which is very important. How many of you have suffered data loss due to a hard disk failure? I myself have suffered twice. It is not a fun situation, right? I'm sure most of you at least once faced a hard drive failure. So, how can you protect your data from hard disk failure or data corruption, etc.? Let's take an example. Let's say you have a photo of your loved ones and you treasure that picture. In your mind, there is no way you can lose that picture. How would you protect it? You would keep copies of your picture in different places, right? Maybe one in your personal laptop, one copy in Picasa, one copy in your external hard drive. You get the idea. So if your laptop crashes, you can still get that picture from Picasa or your external hard drive. So let's do this. Why don't we copy each block of data to 2 more nodes? In other words, we can replicate the block in 2 more nodes. So in total, we have 3 copies of each block. Take a look at this. Node 1 has block 1, 7, and 10. Node 2 has blocks 7, 11, and 42. Node 3 has blocks 1, 7, and 10. So if block 1 is unavailable in node 2 due to a hard disk failure or corruption in the block, it can be easily fetched from node 3. So this means that node 1, 2, and 3 must have access to one another. And they should be connected in a network, right? Conceptually, this is great, but there are some challenges implementing it. Let's think about this. How does node 1 knows that node 3 has block 1? And who decides block 7, for instance, should be stored in node 1, 2, and 3? First of all, who will break the 1 terabyte into 100 blocks? So as you can see, this solution doesn't look that easy, isn't it? And that's just the storage part of it. Computation brings other challenges. Node 1 can only compute the maximum close price from just block 1. Similarly, node 2 can only compute the maximum close price from block 2. This brings up a problem because, for example, data for stock GE can be in block 1 and can also be in block 2 and could also be on block 82, for instance, right? So you have to consolidate the result from all the nodes together to compute the final result. So who's going to coordinate all that? The solution we are proposing is distributed computing. And as we are seeing, there are several complexities involved in implementing the solution, both at the storage layer and also at the computation layer. The answer to all these open questions and complexities is Hadoop. Hadoop offers a framework for distributed computing. So Hadoop has two core components, HDFS and MapReduce. HDFS stands for Hadoop Distributed File System, and it takes care of all your storage related complexities like splitting your dataset into blocks, replicating each block to more than one node, and also keep track of which block is stored on which node, etc. MapReduce is a programming model, and Hadoop implements MapReduce, and it takes care of all the computational complexities. So Hadoop framework takes care of bringing all the intermediate results from every single node to offer a consolidated output. So what is Hadoop? Hadoop is a framework for distributed processing of large data sets across clusters of commodity computers. The last two words in the definition is what makes Hadoop even more special. Commodity computers. That means all the 100 nodes that we have in the cluster does not have to have any specialized hardware. They are enterprise-grade server nodes with a processor, hard disk, and RAM in each of them. That's it. There is nothing more special about them. But don't confuse commodity computers with cheap hardware. Commodity computers mean inexpensive hardware and not cheap hardware. Now you know what Hadoop is and how it can offer an efficient solution to your maximum close price problem against a 1 terabyte dataset. Now you can go back to the business and propose Hadoop to solve the problem and to achieve the execution time that your users are expecting. But if you propose a 100 node cluster to your business, expect to get some crazy looks. But that's the beauty of Hadoop. You don't need to have a 100 node cluster. We have seen successful Hadoop production environments from small 10 node cluster all the way to 100 to 1000 node cluster. You can simply even start with a 10 node cluster, and if you want to reduce the execution time even further, all you have to do is add more nodes to your cluster. That's simple. In other words, Hadoop will horizontally scale. So now you know what is Hadoop and conceptually how it solves the problem of big data sets. With that, let's wrap this lesson and move on to the next lesson. Hey guys, welcome back. In our Understanding Big Data Problem lesson, we saw that HDFS or Hadoop Distributed File System takes care of all the storage related complexities in Hadoop. In this lesson, let's understand more about HDFS. More importantly, why there is a need for another file system like HDFS. Let me start this lesson by asking a question. Have you used any file system before? The answer has to be yes. Just the fact that you're using a laptop or your portable device to watch this lesson, you're using a file system indirectly behind the scenes. File system is an integral part of every operating system. It basically governs the storage in your hard disk. Take a look at this slide. Let's say I give a person a book and I give another person a pile of unordered papers from the same book, and I ask each of them to go to chapter 34. Who do you think will get to chapter 34 faster? The one with the book, right? Because he can simply go to the index, look for chapter 34, look up the page number, and go to the page. Whereas the one with the pile of papers has to go through the pile of papers, and if he is lucky, he might find chapter 34. Just like a well-organized book, a file system helps to navigate the data that is stored in your storage. Without the file system, the information stored in your hard disk will be one large body of data where no way to tell where one piece of information stops and the next begins. Here are some of the major functions of a file system. File system controls how the data is stored and retrieved. Basically, when you read and write files to your hard disk, your request goes through a file system. Next, file system has the metadata about your files and folders. Metadata information like file name, size, owner, created, modified time, etc. File system also takes care of permissions and security. File system manages your storage space. So when you ask to write a file to hard disk, file system helps figure out where in the hard disk it should write the file. And it should write the file as efficient as possible. In the beginning of the lesson, we mentioned that the file system is an integral part of your operating system. So let's look at some of the popular file systems that are already out there. Okay. Although very old, the most legendary file system from Microsoft is FAT32. Maximum file size a FAT32 file system can support is 4 GB. So if you have a file which is 5 GB in size, you're out of luck with FAT32. And it has a 32 GB volume limit or a logical drive limit. So your drive can be of size 32 GB and not more with FAT32. The numbers listed in this slide are baseline numbers, okay? The size limits can be more or less based on the file system configuration. So, if you used Windows 95, 98 or Millennium version, you probably use FAT32. Next generation file system from Windows after FAT32 is NTFS, New Technology File System, and it supports 16 exabyte file and volume limit. 16 exabyte, that is a very huge number, right? Which is 1024 petabyte. So NTFS can clearly support huge volume of data. Starting Windows Server 2012, Windows introduced REFS, Resilient File System. I'm using Windows right now, so how do I know what is my file system? It's very simple to find out actually. Just go to My Computer and select a hard drive. There you go. The file system of my operating system is NTFS, which is shown at the very bottom. So that's how you find a file system in Windows. So going back to the slide, let's look at file systems from Mac. HFS, or Hierarchical File System, is a legacy file system from Mac. Apple started using HFS Plus from Mac OS 8.1 and above. For example, if you used iPod, you would have used HFS Plus. HFS Plus can also handle huge volume of data up to 8 exabyte in size. Next, let's go to Linux. ext is the most popular file system in Linux. ext3 is the third generation file system in use since 2001. Then came ext4. ext4 can support individual file sizes up to 16 terabyte and volumes up to 1 exabyte. Next comes XFS. XFS is created by Silicon Graphics and it can support up to 8 exabyte in file and volume limit. How can you look up your file system in Linux? Let's check it out. Simply log into a Linux terminal and type in df-t. There you go. Here you can see the file system. So ext4 is the file system of this Linux installation. Also, the operating system of this Linux is Ubuntu 14.04 and the file system being used is ext4. So clearly recent file systems can handle individual file sizes up to 8 exabyte or even up to 16 exabyte, right? So clearly we have file systems where we can store big data sets. Then, what is the need for HDFS? Any guesses? No, seriously, take a guess. Let's recap what we learned from the understanding big data problem lesson. We saw that to support truly parallel computation, we had to divide the dataset into blocks and store them in different nodes. And to recover from data loss, we also replicated each block in more than one node, right? Take a look at this slide. Assume you have a 10 node cluster and you have ext4 as the file system on each node, like this right here. We will refer ext4 on each node as the local file system and we will see why. So the first task of your proposed file system is when you upload a file to this proposed file system, you need the file system to divide the data set into fixed size blocks. Although every file system has a concept of blocks, the concept of blocks in HDFS is very different when compared to the blocks in traditional file systems. We'll see the differences in another lesson. Next, your file system should have a distributed view of the files or blocks in your cluster, which is not possible with your local file system, which is ext4 in this slide. What I mean is, your local ext4 file system on node 1 has no idea what is on node 2. Similarly, node 2 has no idea of what is in node 1. Because since the ext4 file systems in both node 1 and node 2 are local to each node, there is no way they can have a global or distributed view of the entire 10 node cluster. That is why we say the ext4 on individual nodes as local file system. Make sense? Next important thing is replication. This adds a lot of complexity, right? Since ext4 in node 1 has no idea about storage in any other node, it does not have the ability to replicate blocks in node 1 to the other nodes. So which means we are exposed to data loss, and that is very bad. So now assume we have a file system on top of ext4, but only this time it spreads across all the nodes. And there you go. We call that file system Hadoop distributed file system. So now when you upload a file to HDFS, it will automatically be split into 128 MB fixed size blocks. In the older versions of Hadoop, the file was divided into 64 MB fixed size blocks. Okay? So HDFS takes care of placing the blocks in different nodes and also take care of replicating each block into more than one node. By default, HDFS replicates a block to 3 nodes. So let's say you copy a 700 MB dataset into HDFS. HDFS will divide the dataset into 128 MB blocks. That is the first step. So you will have 5 equal sized 128 MB block and one 60 MB block. Make sense? So that is a total of 700 MB. Since HDFS has a distributed view of the cluster, it can easily decide which nodes should hold these 6 blocks and also pick the nodes to hold the replicated blocks. HDFS will continue to keep track of all the blocks and their node assignments all the time. So when a user asks about the 700 MB dataset, it knows how to construct the file from the blocks. So let me ask you a question. This is an excellent interview question. Ready? When you have HDFS, what happens to the local file system which is on each node? Take a guess. Here's the answer. HDFS by no means is a replacement for your local file system. Your operating system still rely on the local file system. In fact, your operating system does not care about the presence of HDFS. One more interesting thing. HDFS should still go through ext4 to save the blocks in the storage. As you can see, HDFS is placed on top of the local file system. The true power of HDFS is that it is spread across all the nodes in your cluster. And it has a distributed view of the cluster, and hence it knows how to construct the 700 MB dataset in our example from the underlying blocks. Whereas the ext4 does not have a distributed view and only knows about the blocks in its storage that it is managing. Okay, that explains the need for the new file system like HDFS in a distributed environment like Hadoop. Let's summarize the benefits and functionalities of HDFS. First of all, HDFS supports the concept of blocks. When you upload a file into HDFS, the file is divided into fixed size blocks to support distributed computation. And that is key for Hadoop. Also, HDFS keeps track of all the blocks in the cluster. Second, data failures or data corruption are inevitable in any big data environment, even in small environments, right? So HDFS maintains data integrity. and help recover from data loss by replicating the blocks in more than one node. Third, HDFS supports scaling. That is, if you like to expand your cluster by adding more nodes, it's very easy to do with HDFS. The last one, you don't need any specialized hardware to run or operate HDFS. And this is very important because we are talking about potentially hundreds of nodes. HDFS was built ground up to work with commodity computers. So let's summarize what we learned in this lesson. First, we looked at what is a file system and its functions. And we also looked at the major file systems that are available right now. Next, we talked about the need for a new distributed file system like HDFS and compared a local file system like ext4 with HDFS. And finally, we saw the benefits of HDFS. Okay, with that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. We have now got ourselves introduced about Hadoop. So it is time to try some HDFS commands. You're probably thinking, why are we not talking about name node, data node, etc.? We will most definitely cover those concepts in HDFS architecture lesson later. But I wanted to look at HDFS commands first. Why? We want to use the momentum right away to get our feet wet with some hands-on action. Ready? Okay. I'm logged into our Hadoop cluster. You can get access to the same Hadoop cluster that I'm accessing. If you're registered for the Hadoop in Real World course, you will already have the access. If you're going over the Hadoop Starter Kit course, go to www.hadoopinrealworld.com/starterkit to get your access if you haven't already done so. We ended the last lesson looking at how HDFS is different from the local file system. So let's continue on the discussion. Here are some of the well-known commands to work with your local file system in Linux. You would use mkdir to create a directory, cp to copy, ls to list the contents of the directory, rm to delete, etc. So let's take a look at some HDFS commands. By the way, look at the lessons notes to find the location of this file I'm looking at. Okay? So, all HDFS commands start with Hadoop FS. Before we try a HDFS command, let's try the regular ls command on the root directory, which will bring the files from the root directory in the local file system. You see the files and folders now, right? So here is the HDFS command to list the files from the root directory. As you can see, the output of local file system listing, that is from the top right here, is different from what you see from the HDFS listing right here. That is expected. Why? Because HDFS has a global view of the files in your Hadoop cluster across all the nodes, whereas the local file system can only view or list the files available locally. So let's try the same commands on another node in the cluster and see how it looks. So here I am. I'm logged in to another node in the Hadoop cluster using an admin account, and you don't have access to this node. So in this node, I'm going to try the same two commands, the ls on the root and the Hadoop fs ls command on the root. You can see right away the output of the HDFS listing is same on both the nodes. So we have 4 folders here: benchmarks, temp, user, and var on this node right here. And if you go to the other node, you will see the same 4 folders. But if you look at the ls command on the local file system, the directory structure would be a lot different. You would have files like acoda.group, hirw starterkit, hirw workshop, which you will not see in the other node. This proves that HDFS has a unified global view across all the nodes in the cluster, whereas the local file system does not have a global unified view, and its view is limited to the local file system. So let me clear this screen. Let's try some more HDFS commands. The home directory in your local file system will be /home/the username, right? So there you go. So the username here is hirw user 150430. Whereas the home directory in HDFS is configured to use /user directory as the starting point. So in our case, the home directory for this user in HDFS will be /user/the username that I'm logged in as. When you don't specify the directory name, the listing becomes relative to your home directory. So this command right here and this command right here means the same thing. So let's try both of them. So we have two directories for this user. Let's try the absolute path. There you go. They point to the same exact location, right? Now let's try to create a directory named Hadoop-test1 in HDFS using the mkdir command. The directory is now created. Let's do the listing and check out the directory. There you go. I see it. So we created our first directory in HDFS. So if you do a regular listing in your local file system, you will not see that directory because it is created in HDFS. Make sense? Okay. So it is very clear that the view and the content of HDFS will be different from the local file system. Now let's see how to copy files to and from HDFS. To copy files from the local file system to HDFS, use the copy from local command, like this right here. And to copy files from HDFS to the local file system, use the copy to local command. First, let's copy the file to HDFS using the copy from local. Copy from local takes two parameters. The first parameter is the source location of the file to be copied in the local file system. And the second parameter is the destination location in HDFS where the file will be copied. So let's try this. So with this command, I'm trying to copy a file in location hirw starterkit HDFS commands, this is the file name, to the folder in HDFS. So this file right here is in the local file system. I'm copying this file into a directory in HDFS. The file is now copied to HDFS. Let's make sure. There you go. I see the file under Hadoop-test1 directory. Now let's do the opposite. Let's bring a file from HDFS to local file system using the copy to local command. So as you can see, you would be use copy to local command. You would give the location of the file that you're trying to copy from HDFS as the first parameter, and then the destination location in the local file system as a second parameter. So that's very simple, right? So let's create two more directories in HDFS. So I'm creating two directories, Hadoop test2 and Hadoop test3. The directories are now created. So now let's do a listing. So I have three directories now, test1, test2, and test3, right? I'm going to copy a file from one folder to another. These are very simple commands and easy to follow, right? In the first copy, I'm trying to copy a file from Hadoop test1 directory to test2 directory. So let's try that. The file is now copied. So let's verify real quick. So in this listing, I'm using the relative path. So as I said, by default, your path starts from the user directory if you don't specify the full absolute path. Perfect, I see the file. So now let's move a file from one folder to another. So in this command, I'm going to move the file, not copy, move the file from Hadoop test1 to test3 directory. All right, it is done. So let's do a listing on Hadoop test1. The file is gone from test1 directory because we moved it to test3. So you will see the file in the test3 directory. In our previous lesson, we talked about replication. HDFS replicate each block to more than one node. And this is to help us recover from a data loss. Let's see where we can find information about replication in HDFS. Simply do a listing on HDFS. So currently I'm listing the file under the directory test3. So this number 3 that you see here is the replication factor of this file, meaning this file is divided into blocks and each block is replicated 3 times in the cluster. So the replication factor is set to 3 by default, but you can change the replication factor as you like using the dfs.replication property. So in this command, I'm going to copy a file under test.directory and I'm trying to create a new file with the copy. So while doing so, I'm also set the replication factor to 2. So this will override the default replication factor of 3. So let's try this. So when you do a listing on the new file, you will see the replication factor is set to 2 instead of the default 3. There you go. So this file is replicated only 2 as opposed to the default 3. Next, let's talk about file permissions. Changing file permissions is done exactly as you would do in Linux using chmod. The user who you are logged in as drives the permission in HDFS by default. I'm logged in as this HIRW user. So any files or folders I create, this user will be the owner. So one of the important objectives of this lesson is to understand how HDFS and file system coexist. Take a look at this slide. You may remember from our earlier lesson, when you copy a file to HDFS, the file is divided into blocks, and the blocks are stored in individual nodes. HDFS has a global view of the file even though the file is spread throughout the cluster, whereas the local file system only has a local view of the blocks that it is managing. So many Hadoop learners fail to understand this and miss the local file system involvement here, but not you, because you're taking this course. So when you upload a file, the individual blocks are stored by the local file system in each node. But where? Why we don't see them? Before we look at where the objects are stored, let's get a little more information about the file in HDFS. fsck, the file system check command, is an excellent command and will get you more information about the files or folders in HDFS. You will need sudo privileges to run this command, so you won't be able to execute the command in the cluster. So let's say I want to get more information about this dataset right here, the ELP academic data review.json dataset. So what I'm going to do is I'm going to execute an fsck on this file right here. And I'm going to ask for information about the file, the blocks, and the location of the blocks. So let's try this command. So I'm going to log into a node with an account which has sudo permission. So let me clear this screen. So there you go. The data set is about 1 GB in size. So with a block size of 128 MB, it is divided into 8 blocks, as you can see here, 0 through 7. The replication factor of this file is 3, which you can also see right here. Here you can see that all blocks are replicated properly 3 times on 3 different nodes. Here are the IP address of each node. But if there are blocks which are not replicated 3 times, you can also find that information right here. Next important information you can find is the block name and the location. So here's the block name, and here are the 3 nodes that store this block. Next important information is the status of the file itself. So here you can find this file is healthy because it's fully replicated 3 times. So now we know information about the blocks, the information about the file itself, right? But where are these blocks physically stored? It is stored in the location defined in HDFS site.xml file. HDFS site.xml is an important file which lists the properties important to configure HDFS. This file is usually defined by a Hadoop administrator during cluster setup. In our cluster, you can find this file under etc hadoop conf directory. So here's the HDFS site.xml. Let's open this file. We'll talk more about this file when we talk about the architecture of HDFS. For now, look at this property right here, dfs data node.data.dir. This property defines the location where the blocks will be physically stored in your local file system. To look at this location, again, you need admin rights, so you won't be able to navigate to this folder. But let me show you. Let me switch to the root user. So I'm logged in as root to look at the directory. So let me go into the data node directory and let's navigate even further to get to see the blocks. There you go. So these are individual blocks that are physically stored in your local file system. So when you upload a file into HDFS, HDFS takes the file, divides the file into blocks, and the blocks are physically stored right here. The important thing to understand here is the local file system can only see the blocks, whereas HDFS knows how to construct the file from these underlying blocks. So far we looked at some very important HDFS commands which are very useful to work with the Hadoop cluster. We also understand the key differences between HDFS and the local file system. As you can see, storing a file in HDFS is a lot more involved internally, meaning a file has to be divided into blocks and the blocks has to be stored in various nodes. Plus, it has to be replicated. And when a user asks for a file, HDFS should know how to construct the files from these blocks. So which means it should keep track of all these blocks. That's a lot of work. So some process or processes has to be involved to perform all this work to keep HDFS fully functional. To understand what really happens behind the scenes, we need to understand the components and architecture of HDFS. So that is what we are going to see in the next lesson. See you in the next lesson. Hey guys, welcome back. We now know how to work with HDFS. It's now time to look at the important concepts and processes that make HDFS function properly. In other words, let's learn about the architecture of HDFS. Take a look at this file system check command, fsck. When we try an fsck command on a file or a dataset in HDFS, it gives you the status of the file, whether it's healthy or not, right here. It will also tell you the number of blocks that the file is made of, and not only it will list you the blocks, but will also list you the block locations. That is, the nodes where the blocks are physically stored. For example, this block is replicated 3 times in these 3 nodes. Make sense? Right. So now imagine you're running a 100-node Hadoop cluster, and you have thousands of big data sets in your cluster. All your data sets are divided into blocks, and the blocks are spread across the 100 nodes. Now, when you add replication to the equation, each block will be replicated 3 times. Now, HDFS has to manage the block information and where it is stored. Managing all this information becomes very complex pretty quickly. I keep saying that HDFS has a global distributed view of the file system, and it knows how to construct a file from the blocks. But the question is how? Time for some terminologies. The nodes where the blocks are physically stored are known as the data nodes. And they are named so because these nodes hold the actual data for the cluster. Each data node knows the list of blocks it is responsible for. For example, going back to the output of the fsck command, data node 172.3145217 knows that it is responsible for this highlighted block right here. And similarly, other data nodes knows that it is responsible for the blocks that they are trying to manage. Makes sense, right? But data node misses a key information. It does not know that block ABC and block XYZ belong to dataset 123, for instance, right? So also any given data node knows only about the block it is responsible for and does not care to know about the other blocks in other data nodes. Well, this is a problem for us as users, right? Because we don't know anything about the blocks and we quite honestly don't care about the blocks. All we know is the file name, and we should be able to work only with the file name in your Hadoop cluster. So the question here is, if data nodes does not know which block belongs to which file, then who has that key information? This key information is maintained by a node called the name node. Name node keeps track of all the files or datasets in HDFS. For any given file in HDFS, name node knows the list of blocks that make up the file, not only the list of blocks, but also the location of the blocks. Now you can understand the importance of the name node. Imagine name node being down in your Hadoop cluster. There is no way we can look up the files in your Hadoop cluster because we won't be able to figure out the list of blocks that make up the files. And also we won't be able to figure out the block's location. Other than the block locations, name node also has the metadata of the files and folders in HDFS. Metadata like the owner, size, replication factor, created and modified date times, etc. Due to the significance of the name node, it is also called the master node, and the data nodes are called the slave nodes. Name node persists all the metadata information about the files and folder in hard disk, except for the block location. So, a very good interview question here. Given the block locations is vital for a functioning HDFS, why name node is not persisting that information? Any guesses? Because data nodes have that information. Remember, each data node knows the list of blocks it is responsible for. What it doesn't know, that block X belongs to file ABC. Data nodes and name nodes are in constant communication with each other. So when a name node starts up, the data nodes will try to connect with the name node and broadcast the list of blocks that each data node is responsible for. Name node will hold the block locations in memory and never persist the information in hard disk. Because in a busy cluster, HDFS is constantly changing with new data files coming into the cluster. If name node has to persist every changes to the block by writing the information to a hard disk, it would be a bottleneck. And hence, with performance reasons in mind, the name node hold the block locations in memory, so that it can give a faster response to the clients. So for this reason, you can imagine name node as a powerful node in the cluster in terms of capacity. Now, we know there are two types of nodes in the cluster, name node and data node. We also understand the importance of name node. Name node failure is clearly not an option, but failures in any computer environment is inevitable, and we need to be prepared for that. So when a name node fails, there are recovery strategies. For example, having a secondary name node, and also you can have different cluster configuration like an active standby setup or HDFS federation, which we'll see in advanced architecture chapter. So now you know that for HDFS to function properly, the data nodes and the name node should be in constant communication. So how does the data nodes know the location of the name node? Hadoop has a set of configuration files. In our cluster, the configuration files are under etc hadoop/conf. First, let's look at core site.xml. So let's open that file. This file has a very important property, fs.defaultfs. In this property, we specify the location of the name node. So the name node for this cluster runs on IP 172.3.1.4.5.2.1.6. There are a few other properties in this file for different purposes and may not be HDFS specific. This file is made available to all nodes in the cluster. So any node can look up this property and know the location of the name node. Next important property file is HDFS site.xml. So let's open that file. This file lists all the properties that are specific to HDFS. For example, dfs.namenode.nameDirectory specifies the location in the local file system where namenode can store its files, whereas dfs.datanode.data specifies the location in the local file system where datanode can store its files and physical blocks. Next property is the HTTP address of the name node, which is specified by the property dfs.namenode.http address. So simply copy the value of this property, which is this location right here, and put it in your browser. And you can reach the name node and get details about HDFS. There is another property which you don't see here, which is dfs.replication, which specifies the replication factor of the cluster. That is how many times a block will be replicated in the cluster. The default value for the property is 3. So when you don't see a property in the configuration files, Hadoop substitutes the default value for that property. So in our cluster, the replication factor is 3 since it is the default value. Hadoop is highly configurable, so you can find the list of all available properties in Hadoop's website. And I have included the URL in the lesson notes. As we progress in the course, I'll list all the key properties that you need to know. Next, we have two more important files, master and slaves file. Master's file specifies the name of the nodes where the secondary name node will be started. Slaves file will contain the list of all the data nodes. In our cluster, the slaves file does not have the list of all the data nodes because we started the data node using a script individually on each node. The other property files that you see here are related to other services in the cluster like yarn, etc. Now, if you go to the web URL that we got from the HTTP address, you can find more information about the nodes running in your cluster. You can see the capacity of the cluster. We have 3 live nodes in this cluster and 0 dead nodes, which is good. The location of the name node directory in the local file system right here. You can also list the data nodes too by clicking here. So we have 3 data nodes in our cluster. Under utilities, you can actually browse HDFS and you can also look at the logs. Now you know the configuration details of the cluster. It's time to understand the hardware configuration of the nodes in your Hadoop cluster. The hardware configuration varies from environment to environment and highly dependent on the usage of the cluster. CPU, RAM, and hard disk are the 3 primary elements that make up a node, right? The numbers listed here are just examples and will vary from cluster to cluster. In this example, both name node and data node have 2 quad-core processors each. That's powerful. The important difference between the name node and data node is the memory and the hard disk. The name node is usually high on memory when compared to the data node because it holds a lot of data like block locations in memory. Whereas the data node is high on hard disk space because it has to store the actual data set. Makes sense, right? Finally, all the nodes must be connected in a high-speed network for efficient processing. In this example, we have listed the network as 10 gigabit Ethernet. Now we have an idea about the hardware configuration. Let's get ourselves familiarized with some jargons. What is a rack and what is a cluster? A rack is a group of nodes connected in a network, and a cluster is a group of racks connected in a network. So all your nodes in the clusters are connected. Next, what is a data center? A data center is a physical location where a cluster is housed. Some years back, data centers used to be dark and ugly, but these days data centers are state of the art. Here is the inside of Facebook's data center located in Oregon. Beautiful, isn't it? And here is the inside of Yahoo's data center. Neat and well organized. And here's the outside of Facebook's data center. We learned a lot in this lesson, so let's summarize. We talked about the functionalities of the name node and the data nodes. We looked at HDFS specific configuration properties and also hardware configuration for both name node and data nodes. Finally, we saw that a cluster is made up of racks and racks are made up of individual nodes connected in a network. So with that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. By now, you're quite familiar with HDFS. It is now time to learn about MapReduce. So in this lesson, we're going to learn about the basic concepts of MapReduce. But I'm not going to bore you with the word count problem. We're going to learn the MapReduce concept using a fun example. Ready? Okay, let's pick a state, California. Imagine for a second, the governor of California comes up to you and make you the head of Census Bureau for the state of California. And you are tasked with finding the population of all cities in California. You have all the resources you want, but you have only 4 months to finish the task. Think about this for a second. How would you proceed with this task? Remember, you can have all the resources you want. What would be your process? Calculating the population of all cities for a big state like California is not an easy task for any one person, right? So the sensible thing to do is to divide the state by city and make individuals in charge of each city to calculate the population of each city he is in charge of. Just for illustration purpose, let's focus on only 3 cities: San Francisco, San Jose, and LA. Person 1 will be in charge for SFO. Person 2 will be in charge for San Jose. And person 3 will be in charge of LA. Okay, so far so good, right? You have divided the California state into cities and each city is assigned to a person. And he is responsible for finding the population of the assigned city. You now need to give instructions to each person on what they have to do. So you ask each person to go to a home, knock on the door, and when someone answers the door, ask how many people live in the home and note it down. You give them specific instruction on what each person should note down. You're instructing each one to note down the city they are responsible for and the number of people live in the home. Then the person has to go to the next home and repeat the same process until he covers all homes in the assigned city. Make sense? So, for a person who covers SFO, he goes to first home. There are 5 people in the home, so he note down SFO 5. 3 people are living in the second home, so he note down SFO 3. You get the idea, right? It is a classic divide and conquer approach. Same instructions will be carried out by everyone involved. Person 2 will go to San Jose, and person 2 will do the same in LA. When each person is done with their assigned city, you ask them to submit their results to the state's headquarters. You'll have a person in the headquarters to receive the results from all cities and aggregate them by city to come up with population of each city for the entire state. Very simple process, right? So 4 months in, With this strategy, you're able to calculate the population of California. The governor who assigned this task to you is so happy, right? Next year around, you're asked to do the same job. You have all the resources you want, but this time you have 2 months to finish the task. What would you do? Remember, you have all the resources you want, so you would simply double the number of people to perform the task. You will divide SFO into two divisions and add one person to each division. And you will do the same thing for San Jose and same for LA. Each person responsible for a division will perform the same task as before. You can also do the same thing at the headquarters. Let's divide the headquarters into two. California headquarters 1 and California headquarters 2. And one person to each division. Perfect. With twice as much people, you can finish the task in half the time. But there is one small problem. You want the census takers for SFO, that is SFO1 and SFO2, send their results to either California headquarters 1 or headquarters 2. You don't want SFO1 sending results to California headquarters 1 and SFO2 sending their results to California headquarters 2, because this would result in population count for SFO divided between headquarters 1 and 2. That is not ideal, right? Because we want consolidated population count by city, not partial counts. So what we can do? Simple. We can instruct census takers in SFO 1 and 2 to send their results to either headquarters 1 or headquarters 2. Similarly, we should instruct census takers for San Jose and LA. They should either send it to headquarters 1 or 2. Problem solved. You try with this model and again you did it. You were able to complete the census calculation in 2 months. If next year, if you were asked to do the same thing in a month, you know exactly what to do. And you can simply double the resources and apply your model and it will work like a charm. You now have a good enough model. Not only the model works, but it also can scale. That is it. The model you have here is called MapReduce. MapReduce is a programming model for distributed computing. It is not a programming language. It is a programming model which you can use to process huge data sets in a distributed fashion. Now let's look at the phases involved in MapReduce. The phase where individuals collect the population of their assigned city or part of the city is called the map phase. The individual person involved in the actual calculation is called the mapper. And the city or the part of the city he is working with is known as the input split. The output from each mapper is a key value pair. As you can see, the key is SFO, the value is 5, or the key is San Jose, the value is 2. The phase where you aggregate the intermediate results from each city or mappers in the headquarters is called the reduce phase. And the individuals who work in the headquarters are known as the reducers because they reduce or consolidate the output from many different mappers. Each reducer will produce a result set. The phase in which the values from the different mappers are copied or transferred to reducers is known as the shuffle phase. The shuffle phase comes in between map and the reduce phase. So, the map phase, shuffle phase, and reduce phase are the three phases of MapReduce. We'll look closer into each phase in the next lesson, where we'll talk more about entities like combiner, partitioner, etc. Okay, so let's summarize what we learned about MapReduce. MapReduce is a distributed programming model for processing large data sets. So this concept was conceived at Google, and Hadoop's adapt this programming model. It can be implemented in any programming language, and Hadoop supports a lot of programming language to write MapReduce programs. You can write a MapReduce program in Scala, Python, C++, and of course Java. MapReduce is not a programming language. It is a programming model. So always keep that in mind. Of course, Hadoop implements MapReduce. So the MapReduce system in Hadoop manages the communications, data transfer, parallel execution across the distributed servers or nodes. So in this lesson, you got introduced to the concept of MapReduce And you also know the phases involved in MapReduce. So in our next lesson, we'll go over each phases in detail. And then we'll try to write a MapReduce program in Java, one step at a time, okay? With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. In the last lesson, we looked at the concept of MapReduce, and we also talked about the different phases in MapReduce. In this lesson, we'll take a real example and we'll walk through the process involved in each phase of MapReduce. Here's a problem we like to solve today. We have a data set with information about several fictitious stock symbols. In each line in the data set, we have information about a stock symbol for a day. Information like the opening price, closing price, high, low, volume, etc. So here is the data set. So let's pick a line here. So this is going to be our record. So the first is the exchange name, ABC Stock Exchange. The next is the symbol, the date, the opening price, closing price, high, low for the day, and the volume. Very simple data set, right? So this data set is about 400 MB. Not too big, but good enough for our experimentation and learning. Now let's talk about the problem we would like to solve with this data set. For every stock symbol in the data set, we would like to find out its maximum closing price across several days. Simple use case, right? So now think about this problem for a second. Forget about MapReduce and Hadoop. How would you go about to solving this problem? Just think about the algorithm. Ready? Let's look at the algorithm. We'll read a line, get the symbol and closing price from the line. Then we need to check if the closing price is greater than the closing price we have for that symbol. If not, go to the next line. If the closing price is greater than the closing price that you already have for that symbol, save the closing price as the maximum closing price for that symbol and move on to the next record in the dataset. If you reach the end of the file, very simple, print the results. Now the problem with this approach is that there is no parallelization. So if you have a huge data set, you will have extremely long computation time, which is not ideal. Now let's see how we have worked out the same problem in the MapReduce world. From the last lesson, we got introduced to the phases of MapReduce. So we'll take this problem and go over each phase and see the technical details involved in the map phase, reduce phase, and shuffle phase. Let's first talk about the map phase. The central idea behind MapReduce is distributed processing. So the first thing is to divide the data set into chunks. And you have separate process working on each chunk of data. Let's assign some technical jargons now. The chunks are called input splits, and the process working on the chunks are called mappers. Each mapper would process a record at a time. And each mapper would execute the same set of code on every single record. The output of the mapper would be a key value pair. First, what is an input split? How many of you think input split is same as the block? Input split is not same as the block. A block is a hard division of data at the block size. So if the block size in your cluster is 128 MB, each block for the data set will be 128 MB, except for the last block, which could be less than the block size if the file size is not entirely divisible by the block size. Make sense? Since a block is a hard cut at the block size, a block can end even before a record ends. Let's look at this in detail. Consider this. In our example here, we have 4 records in our dataset, and each record is 100 MB. And the block size of our cluster is 128 MB. So the first record will perfectly fit in the block, no problem. Since the record size is 100 MB, it's well within the block size, which is 128 MB. However, the second record cannot fit in the block. So the record number 2 will start in block 1 and will end in block 2. If you assign a mapper to block 1, in this case, the mapper cannot process record 2 because block 1 does not have the complete record 2. This is exactly the problem input split solves. In this case, input split 1 will have both record 1 and record 2. Input split 2, however, does not start with record 2, since record 2 is already included in the input split 1. So input split 2 will have only record 3. As you can see, record 3 is divided between block 2 and block 3. Input split is not physical chunks of data. It is a Java class behind the scenes with pointers to start and end location within blocks. So when a mapper tries to read the data, it clearly knows where to start and where to end. The start location of an input split can start in a block and can end in another block. So that is why we have a concept of input split. Input split respects logical record boundary. During MapReduce execution, Hadoop scans through the blocks and create input splits which respects record boundaries. Now that we understand the input to each mapper, let's talk about the mapper itself. A mapper in Hadoop can be written in many different programming languages. It can be written in C++, Python, Scala, and of course Java. So in our case, we'll look at Java. So a mapper is a Java program in our case, which is invoked by the Hadoop framework once per every record in the input split. So if you have 100 records in your input split, the mapper processing the split will be executed 100 times. Now I have a question for you. How many mappers do you think Hadoop will create to process a dataset? Ready with an answer? The number of mappers is entirely dependent on the number of input splits. If there are 10 input splits, there will be 10 mappers. If there are 100 input splits, there will be 100 mappers. So a mapper is invoked for every single record in the input split. And then what? The output of the mapper should be a key value pair. In our sample stock dataset, every line is a record for us. And we need to parse the record to get the stock symbol and the closing price. So the stock symbol and the closing price becomes the output from each execution of the mapper. The symbol is going to be the key, and the closing price is going to be the value in your key value pair. But how do you decide what should be the key and what should be the value in your key value pair? Let's look at the reduce phase. That will give us an answer. The reducers work on the output of the mappers. The output of individual mappers are grouped by the key, in our case the stock symbol, and passed to the reducer. Reduce will receive a key and a list of values for that key for input. As I said, the keys will be grouped. So let's say our data set has stock information about 10 stock symbols and 100 records for each symbol. So that is 1000 records in total, right? 10 stock symbols and 100 records for each stock symbols. That is 1000 records. So you will get 1000 key value pairs from all mappers combined because your mapper will be executed for each record. When processing a record, you can decide not to output a key value pair for the record. For example, the record could be bad, for instance. In that case, you won't output a record from the mapper. But in an ideal scenario, you will have 1000 key value pairs because you have 1000 records. Then the reducer will receive 10 records to process, 1 record for each symbol, since we only have information about 10 stocks. Make sense? Each record for the reducer will have a symbol for the key and a list of closing prices for value. That is all you need to calculate the maximum closing price for each symbol, correct? The work of the reducer becomes simple. It reads the key and calculates the maximum closing price from the list of closing prices for that symbol and output the result. So going back to our question, how do you decide what should be the key and what should be the value? I'll give you a simple trick. Whenever in doubt, think about what needs to be reduced. In our example, we know if the reducer has the stock symbol and the list of closing prices for a given stock symbol, we can arrive at the maximum closing price. Also, we want the reducer to be called once per symbol. That is why we made symbol as the key in mapper's output and closing price as the value. One more question. We know the number of mappers equals to the number of input splits and not controlled by the users. What about the number of reducers? The number of reducers can be set by the user. You can even have a MapReduce job with no reducers. Let's say your data set is divided into 100 splits, which means 100 mappers, right? Now you have only one reducer to process all the output from 100 mappers. In some cases, it might be okay, but you might run into performance bottleneck at the reduce phase because you're trying to reduce output from 100 mappers in one reducer. So if you're dealing with large amount of data in the reduce phase, it is advisable to have more than one reducer. In this slide here, we have multiple reducers. Now you have a good idea about the reduce phase. Now let's look at how the output of the individual mappers got grouped by symbols and reached the reducer. The magic happens in the shuffle phase. Shuffle phase is also a key component in MapReduce. The process in which the map output is transferred to the reducers is known as a shuffle. Let's walk through the shuffle phase in detail. Let's say in our MapReduce job, we decided to use 3 reducers. Let's say you have data for Apple in the stock data set. And we have 10 input splits to process, which means we will need 10 mappers. We can have records for Apple in more than one input split, right? Let's say the records for Apple is spread out in all the 10 input splits. This means each mapper will produce key value pairs for Apple in its output. When you have more than one reducer, you don't want the key value pairs for Apple to be spread out between the 3 reducers. That will be bad for our use case because we won't be able to calculate the consolidate max closing price for Apple, correct? So we want all the key value pairs for Apple to go to one reducer. In other words, we want each key or symbol in our case to be assigned to a reducer and stick with it. In the map phase, each key is assigned to a partition. So if you have 3 reducers, you will have 3 partitions. And each key is assigned to a partition by a class called partitioner. So if the partitioner decides that any key value pair with Apple as key should go to partition 1, then all key value pairs with Apple as key will go to partition 1. And each partition will be assigned to a reducer. Partition 1 will be assigned to reducer 1, partition 2 will be assigned to reducer 2, etc. It is key to understand that this partitioning happens across all the mappers in the map phase. Hadoop framework guarantee that input to the reducers is sorted by key. And so once the keys are assigned to the right partition, the key value pairs in the partition are sorted by key. Once the keys are sorted, we are now ready to copy each partition to the appropriate reducers. This is known as the copy phase. You have to understand that data for partition 1, for instance, can come from many mappers. Because in our example, the records for Apple can be spread across multiple input splits. So in the reduce phase, the partitions have to be merged together, maintaining the sort ordering by key. Even though the intent sorting happened at the map phase, in some documentation you will see the merge action referred to as sort on the reduce side. So once the reducers have received all the partition from all the mappers and the partitions are merged, the reducer will perform the actual reduce operation. So that's the shuffle phase. Let's summarize the shuffle phase. Each mapper will process all the records in its assigned input split and will output a key value pair for each record. If you look at the output, we have symbol for a key and closing price as value. For example, you can see here ABC is the symbol and 60 is the closing price for ABC. Similarly, for symbol STT, we have closing price as 82. Same for other mappers as well. You may also note that symbols in mapper 1 can also be found in mapper 2. Look at the symbol STT for instance. You have STT in mapper 1 and you can also see STT in mapper 2. Then in the shuffle phase, within each mapper, the key value pairs will be assigned to a partition. Within each partition, the key value pairs will be sorted by key. As you can see in the slide, the output key value pairs are nicely sorted by key in each mapper. Then the key value pairs from each mapper will be copied over to the reduce phase, to the appropriate reducers. At each reducer, the key value pairs coming from different mappers will be merged, maintaining the sort order. There are two things to note in the slide. First, the symbols are unique to each reducer, meaning even though records from symbol were widespread across multiple mappers, they were sent to one reducer. Take a look at symbol ABC for instance. ABC was found in mapper 1 and ABC was also found in mapper 2. But key value pairs for symbol ABC is sent to only one reducer, in this case reducer number 1. Similarly, you can find key value pairs for symbol STT in mapper and also in mapper 2. But the key value pairs for STT is sent to only one reducer, in this case reducer number 2. Once the key value pairs are copied and merged, the job for reducer is very simple. Reducer 1 will run 3 times, one for each symbol, and reducer 2 will run 2 times, once for each symbol. Each run will print the symbol and its maximum closing price. That's the end-to-end process in MapReduce. We could also have an optional combiner at the map phase. Combiners can be used to reduce the amount of data that is sent to the reduce phase. In our example, there is no reason to send all the closing prices for each symbol from each mapper. For example, in mapper 1, we have 3 records for symbol ABC. One record with closing price 60, one record with closing price 50, and one record with closing price 111. Since we are calculating the maximum closing price, we don't have to send the key value pairs with closing price 50 and 60 because they are less than the closing price 111. So all we need to do here is we need to send the key value pair with closing price 111 for symbol ABC from mapper 1 to the reducer. If you think about it, combiner is like a mini reducer that runs at the map phase. Combiners can be very helpful to reduce the load on the reduce side, since you're reducing the amount of data that are being sent to the reducers, thereby increasing performance. Combiners are optional. I have a question. Think about this. Can you use a combiner in all scenarios? We will save that question for another lesson. So to summarize, in this lesson, we talked about the internals of map, shuffle, and reduce phases. And finally, we looked at the benefit of using a combiner. With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. Now we have a very good idea about the phases involved in MapReduce. Also, we have a very good conceptual understanding of what is a mapper, reducer, combiner, etc. Now to the fun part. Let's go ahead and write a MapReduce program in Java to calculate the maximum closing price by stock symbol from our stock dataset. Here is the game plan. We're going to write 3 programs: mapper, reducer, and driver program. We know what a mapper and a reducer is, but what is a driver program? So let's start with that. I have the project created in Eclipse already. So this project, Maximum Close Price, is a Mavenized project. So I have all my dependency jars in pom.xml. So in the pom.xml, as you can see here, I have included all the needed Hadoop jars. So you can see all the Hadoop jars are included by Maven into your project, so you don't have to worry about the dependencies. This is a typical Java project, so there is nothing special about it. Okay. Open the source folder. I have 2 packages, com hirw max close price and com harw max close price.test. So under the first package, I have three programs. One is the mapper, max close price mapper.java. The second one is the reducer, max close price reducer.java. And the third one is the driver program, which we are going to see now. All right, so let's open the program. Here you go. A driver program will bring all the needed information together to submit a MapReduce job. So what is the information you need to submit a MapReduce job? The first thing is, to submit any MapReduce job, you need to know the input location, that is the location of your input data set, the output location where the MapReduce job should output the result set. You should also provide the mapper that should be executed. You should also provide the reducer that needs to be executed, if there is any, right? So let's go one by one. Job object refers to a MapReduce job. Instantiate a new object and give a name to the job. When we run this job on a Hadoop cluster, we'll package the code into a jar, which we'll see in a bit, and Hadoop will distribute the jar across all nodes in the cluster. So Hadoop needs to know how to locate the jar file, right? So that's why we have the second line here, which is job.setJar by class. You give the class name, that is this class name max close price, as an argument to this method, and Hadoop uses this class to locate the jar file. In the next couple of lines, you will set the input path where you find the input data set and the output path where this job should write the output. So you will set the input path in the file input format class. There is a function add input path to give the location of the input path. So the first argument is the job itself, and the second argument is the location of your input path. So when you're running the program, you pass two arguments to the program, right? The first argument is going to be the location of the input data set, and the second argument is going to be the location of the output data set. The next step is to let your Hadoop job know what is the format of your input data set and the output data set, which you will do by setting the input format class and setting the output format class on the job object. So let's look at input format first. Input format is responsible for three main tasks. First, it validates the inputs, meaning make sure the dataset already exists in the location that you specify. Next, split up the input files into logical input splits, each of which, that is, each of the input split is then assigned to an individual mapper. Finally, and this is important, input format provides record reader implementation to extract input records from the logical input split for processing by the mapper. In our case, our stocks data set is of text format and each line in the data set is a record. So we'll use the text input format class as the input format for this job. Hadoop provides several other input formats and each designed for specific purpose. For example, if your data set has binary key value pairs, you can use sequence file input format. And there are several other important file formats that are in use today, like file formats for Avro, sequence, RC file, etc. In fact, due to its importance, we have a separate chapter dedicated to file formats. Furthermore, we'll also look at implementing a custom file format in the later chapters. Similar to the input format, output format validate the output specification, meaning is the output directory specified already exist. If it already exists, it will throw you an error, because when you run a MapReduce job, Hadoop doesn't want to by mistake overwrite the existing output directory or any other directory, right? So it's kind of a safety check. So the first check is validate the output specification, make sure that the directory that you specified for the output doesn't exist. So Hadoop can create it while generating the output. The next thing output format has is a record writer implementation that is to be used to write out the output files for the job. So input format has a record reader implementation, whereas the output format has the record writer implementation. Makes sense, right? One is to read and the other one is to write. Again, just like the input format, Hadoop comes with several output format implementation. In fact, for every input format, you can find a corresponding output format. And also you can write custom implementations of output format as well. So now we talked about input format and output format. Next, in the driver program, you have to specify the mapper class and the reducer class. So I've already returned the mapper, which is max close price mapper, and the reducer is max close price reducer. So I've specified what is my mapper and what is my reducer for this job on the job object using the method set mapper class for the mapper and set reducer class for the reducer. You also need to set the output key value types for both your mapper and reducer. The output key from your mapper and the output key from your reducer in this case or for this program is of type text. And the value in your key value pair, that is the output value from the mapper and from the reducer, is of type float writable. These types certainly look new, doesn't it? Yes, they are. There are writable wrappers in Hadoop for all major Java primitive types. For example, the writable implementation for int is int writable, for float is float writable, for boolean is boolean writable, and for string it is text. But why new data types when we already have well-defined data types in Java? Writables are used whenever there is a need to transfer data between tasks. That is, when the data is given as input and output to and from mappers, also when the data is given as input and output to and from the reducers. As you know, Hadoop is a distributed computing framework, which means you will have mappers and reducers distributed in many different nodes. And this means you will have a lot of data being transferred between nodes. So when there is a need to transfer data over the network between the nodes, the object must be turned into a byte stream. And this process is known as serialization in Java. As you can imagine, Hadoop is designed to process millions and billions of records. So there is a need to transfer a lot of data over the network. And hence, serialization should be compact, fast, and effective. Make sense? But the authors of Hadoop felt that Java's out-of-the-box serialization was not that effective in terms of speed and size. Here are a couple of reasons why they felt so. You see, Java serialization writes the class name of each object which is being serialized to the byte stream. This is to know the object's type so that we will be able to deserialize the object from the byte stream later, right? So, and every subsequent instance of the class should have the reference to the first occurrence of the class name. So as you can see in the slide, we have three instances of employee object, employee 1, 2, and 3. And the first instance clearly has the name of the class. The second and the third instance refer to the same name. So it must have reference handle to the name. This reference results in two problems. The first one is the space, and hence it cannot be compact because it is adding more space. The second problem is that the reference handles introduce a problem during sorting records in a serialized stream. As you know, during the shuffle phase, the key value pairs are being sorted by key. So sorting is a key element in MapReduce. Since only the first record will have the class name, it must be given special care. So writables was introduced to make the serialization fast and compact. How? By simply not writing the class name to the stream. Then, if you don't write the class name to the stream, how would you know the type during deserialization? The assumption is that the client knows the type. So whoever is writing it will know what the type of the serialized object is. And this is usually true. And there is one more benefit of using writables as opposed to regular Java types as key value pairs. With standard Java types, when the objects are reconstructed from a byte stream during the deserialization process, a new instance for each object has to be created. Whereas with writables, the same object can be reused, which improves processing efficiency and speed. Later, we are going to look into how to write custom writables in a very interesting example. So if you logged into LinkedIn or Facebook, you would see like your common friends, right? So if you're looking at a friend's profile, you will see what are all the friends that you and your friend have in common. So we'll look into the common friends problem and how we can address that problem using MapReduce. When we do that, we'll talk about custom writables. Okay, moving on. Back to our driver class here. The job wait for completion method submits the job and also wait for it to finish. You can set the Boolean argument to true so that you can see the progress of the job on the console. So that's our driver program. Guys, let's pause right here. We'll continue our discussion in the next lesson where we'll look at the mapper program, the reducer program, and execute the MapReduce job in our cluster. Let's move on to the next lesson. Hey guys, let's continue from where we left off. We looked at the driver program in detail. We are also now familiar with the input and output format and writables. In this lesson, we'll look at the mapper program, reducer program, and execute the MapReduce job in our cluster. Let's now move on to the mapper. So here's my mapper program, maxClosePriceMapper.java. Before we talk about the mapper program, let's recap what is a mapper and what is a map face. So your data set will be divided into multiple parts, and we call the parts input splits because input split respects logical record boundaries. Each mapper then processes an input split. Each mapper will be called multiple times depending on the content of the input split. Meaning, if you have 100 records in the input split, each mapper will be called once for each record. So in our case, it's going to be 100 times. The output of the mapper for each record will be a key value pair. A mapper for a given run can choose not to write an output. For example, if it is processing a bad record, it can choose not to write a key value pair as output for a specific run processing a record, and that is okay. There will be one or more mappers in a MapReduce job, and the number of mappers is determined by the number of splits. Make sense? Let's now go look at the program. In our dataset, that is our stock dataset, each line is a record to the mapper. So a mapper will be called once for each line in the input split. Let's talk about the output from the mapper, that is the actual output. Right? So in this problem, we're trying to find out or calculate the maximum closing price for each stock symbol. This means that we have to group the records by symbol so that we can calculate the maximum closing price by symbol. So we will output the stock symbol as the key and close price as the value for each record. Make sense? So that's going to be our key value pair. Our key is going to be the stock symbol and the close price will be the value for the key value pair. Okay, we now know what is going to be the map's input and what is going to be the map output. Let's look into the program. We'll extend the mapper class to make our class a mapper. Make sure you have the right import. So the import we are using here for the mapper class is org.apache hadoop mapreduce.mapper. The older version of Hadoop library will have MapRed instead of MapReduce as a naming convention for the package. Whereas the later version or the latest version will have MapReduce as a naming convention. Make sure you have included the MapReduce to avoid any class conflicts. Look at the signature of the mapper class. There are 4 parameters listed here. The first 2 parameters dictate the input to the mapper as key and value. The third and the fourth parameter tells us the output key and value types from the mapper. So the input key to the mapper is of type long writable and the input value is of type text. The output key from the mapper is of type text and the output value from the mapper is of type float writable. In our program, we have to override the map method because this method will be called for every record that is passed to the mapper. The first 2 arguments of the map method varies based on the input format that defines your dataset. The second parameter, what we have here, makes sense, right? The type is defined as text, which is the actual line from the file. The first argument, however, is long writable, but what does it really represent? The first argument is the byte offset of the record within the file from the beginning of the file. So this argument, in this case, is not much of importance to us. So we will just ignore the argument when we are processing the record. because we are more interested in the second argument, which is the actual record from the file. The value that is passed into the map method has the actual stock record. So if you go back to our data set, this is our data set, right? So every single line is a record for us. So for example, in one of the mapper runs, this record will be passed to the mapper. As you can see, the record is delimited by comma. So the first thing we'll do is take the value object and convert it to a string so that we can manipulate the record as a string, which is much easier. We also know our data set very well. And here we are looking to extract the symbol and the closing price from each record. We know by looking at the data set, the second column has the symbol and the seventh column is the closing price. Since the index of the column starts from 0, we have to use 1 and 6 to extract the symbol and the closing price. Now we have two values from the record that we are most interested in. We know that the output of the mapper should be a key value pair. In our case, the symbol will be the key and the closing price will be the value. But how do we submit the output from the mapper? We will use the context object to set the key value pair. That is it. From here on, Hadoop will take care of the output. The output along with the other key value pairs from other mappers will be sorted and partitioned by key, which will then be copied to the appropriate reducer. Then, at the reducer, the output from several mappers will be merged. The values for a key will be grouped, and the input to the reducer will be a key with list of values for that key. The reducer will be called once per key. Before we take a look at the reducer, let's recap what a reducer is. A reducer or a reduce function is going to take key value pairs from multiple map functions as input and reduce them to output. The keys are grouped with values. And the reduce function is called once per key and its values. So for example, in our case, the key value pair is symbol and closing price. So the key value pairs from all the mappers will be grouped together by the key, in this case the symbol. The reduce will receive 10 records to process, one for each symbol, right? So each symbol will have a list of values, the values being the closing price. Make sense? So in your MapReduce job, you can have 0, 1 or more reduce function. So how many reducers you can have for your MapReduce job? You can have 0, 1 or more reducers. In our case, we definitely need a reducer. In some cases, you may not need a reducer because you won't be reducing anything. You can output the results straight from the mapper. In some cases, reducers may not be necessary, but in our case, clearly, we need a reducer. Now let's look at the reduce program. So here's our reduce program. Having seen the mapper already, following the reducer will be much easier. First, start by extending the reducer class. You have to specify 4 type parameters. The first 2 parameters define the input to the reducer, and the third and the fourth defines the output from the reducer. Next, override the reduce method. This will take text as the key, which is nothing but the stock symbol, and an iterable list of float writables, which is nothing but the list of closing prices for that particular stock symbol as arguments. Once you have the list of closing prices, it is easy to calculate the maximum closing price. So you simply iterate through the list and calculate the maximum. Use the math.max function to compare two values and find the maximum closing price between the two. Finally, once you have the output, simply submit the output by calling the right method on the context. Now we have the program ready. It is now time to run this MapReduce program as a job in our Hadoop cluster. So to do that, we need to export this project as a runnable jar. Let me show you how to do that. So just right click on the project. It's very simple. Click on export, jar file, next, give a location. You can save it anywhere and hit finish. That's it. Your jar file is now saved. So I have saved in this location right here. To run this jar in our Hadoop cluster, you need to first copy the jar into our Hadoop cluster. Since I'm using Windows, I use a software called WinSCP, which is a free software. You can download it from the internet. So open the software, hit new, give the host name, which is our IP address for the cluster, give your username. You don't need to give the password, but you need to give the private key file which was provided to you. Okay, and save it for future reference. So I've already saved such a reference. So I've already saved my credential. So I'm going to use that credentials to open up a session. I'm going to use this connection right here, login. So depending on the course you're taking, you may have some restrictions on the cluster. So if you're taking the starter kit course, you may not be able to copy any files into your home directory. But if you're taking the Hadoop in real world course, you will be able to copy, just drag and drop the jar file into your home location. But don't worry if you're taking the starter kit course. I've already copied the jar into a location where you can access. And same for the other course as well. So look at the lesson notes for the exact location of the jar file. So as you can see, if you go to the root directory, there are two folders, one for starter kit, one for workshop. So if you're taking the starter kit course, go to the starter kit folder. And if you're taking the Hadoop in real world course, go into the workshop folder. So let me go into the starter kit, right? So go into MapReduce, click on stocks, and here you go. I have the jar right here, and I also have a README file. So open the README file, right? It doesn't matter what course you're taking, you can find the location in the lesson notes. It's all in the cluster, so don't worry, okay? You can either view the files using WinSCP, or you can also use the Linux terminal, whichever is comfortable for you. There you go, you see the jar file and the README file, so you can open the README file from here as well using VI. It's totally up to your convenience. So let's look at how we can submit the job, okay? So the first thing is the input location. I've already uploaded our stocks dataset to this HDFS location right here, user HIRW input stocks. This dataset is about 400 MB, okay? The output location that we're going to write is output MapReduce stocks. See, we don't have a slash in front, so which means this location is going to be relative to the user. It's always a better practice to delete the output directory first, because if the output directory already exists on HDFS, when you run your MapReduce job, Hadoop will complain that the output directory already exists. So you may want to clean up the output directory if it's already there before you kick off a Hadoop job. All right, the next is the Hadoop command to actually run the MapReduce job. Use the Hadoop jar command followed by the jar location and give the class name to start. That is the class which you want to first execute. So we are giving the driver program here because we have the driver program has all the information to submit the MapReduce job into your cluster. Followed by two arguments. The first argument is actually the input location, that is the input location of the stock dataset. And then the second argument is the output location where you want to write your output. You may want to note that we are using Hadoop to execute the jar file instead of using Java to execute the jar file, because using Hadoop conveniently adds all the Hadoop libraries to the class path. If we decide to use Java to execute, we can do that, but then we have to manually specify all the classes that are needed to be added to the class path. So using Hadoop is a much better choice because it's convenient. So the first thing I'm going to do is I'm going to clear the output directory, just to be sure. All right, so there's no such directory, so I'm good to go to run my MapReduce job. You can see the progress of the MapReduce job because it's going to print the information of execution on the console. The first thing you will see here is the number of splits for. I said it's a 400 MB data set. With 128 as the block size, we resulted in 4 input splits. So which means we would need 4 mappers. There you go. We have processed 400 MB in just a matter of seconds. Okay, so let's look at a few more things before we look at output and a few other things, right? So you will see a lot of information that is displayed on your screen. You can also see the progress that is being made. The map and the reduce started with 0%, then map went to 75 to 100, and then map and reduce finished with 100% each, right? So the next important information is, of course, the job completed successfully, right? And you're seeing few counters. Counters are useful information to see what is going on when you execute a MapReduce job. Here are some key information that you want to look for. The first one is launched map task. So we have launched 4 map tasks and we have launched 1 reduce task. And the number of input records to the map, which is about 7,461,349 records. So we processed 7 million stock records. And the map outputted the same number of records because for every record, we extracted the symbol and the close price. And the next important thing is reduce input groups, which is the number of records sent to the reducer. In this case, it's 836, which means we had 836 unique symbols or unique stock symbols in our dataset. And the reduce output is also the same because for every symbol, we want to know the maximum close price. So that is it. So those are some of the key important counters you may want to look at. But there is much more. Counters are very helpful, especially when you had a bad executing job. When the output doesn't match your expectation, you can always refer to the counters and see how many records are processed, whether there are any issues, and things like that. Since our MapReduce job is now complete, we can now actually look at the output. So I'm just printing the output on the console. So it's 836 records, as you can see. Each symbol has a closing price. And this closing price is the maximum closing price of each symbol. So now we were able to successfully execute a MapReduce program to calculate the maximum closing price by symbol. And here's our output, right? There's one more thing I want to show you, and then with that, we'll end this lesson. So you can also look at the status of the MapReduce job as it's executing in your cluster using this URL right here. So this URL is specific to this application, that is specific to this MapReduce run because it has the actual application ID. So copy this URL and paste it in your browser. You can see all the information that you saw on the screen in this URL. So some of the important information that I want to show you is basically the number of maps that ran, which is 4, the number of map attempts and reduce attempts. There are no failures and no mappers or reducers were killed during execution, which is a good thing. The state is success, which we know already. So let's click on the 4 mappers, as you can see. So these are the 4 execution, each execution successfully completed. You can also look at the attempt number and also look at the node in which the mapper was executed. That is it. We successfully executed our first MapReduce job. With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. In the last few lessons, we learned a lot about HDFS, MapReduce, and we also wrote a MapReduce program to calculate the maximum closing price of each stock symbol in our stocks dataset. Even though the MapReduce program we saw was simple and easy to understand, we can agree that writing MapReduce program takes some effort. In the very least, you need to understand the concept of MapReduce. You need to know the basic understanding of different MapReduce phases. You need to know a programming language like Java, Python, or Scala to write a MapReduce program. And finally, and the most important thing is to visualize the problem in MapReduce. And that takes some practice. But once you're done with the program, you need to test it with a smaller data set in a dev or test cluster. And then when all checks out, you then deploy your MapReduce program into production. This obviously takes a lot of time and effort, and not to mention some learning curve. Let's take our maximum closing price by stock symbol problem. Wouldn't it be so awesome to have a tool that takes in few instructions and execute them in our Hadoop cluster and get us the same output? You know where I'm going with this. Apache Pig is our answer. Pig was developed at Yahoo to make MapReduce accessible to anyone who want to work with Hadoop cluster. Pig is now a top-level project in Apache. Pig is widely used in the industry and a must-know tool if you would like to get involved in the Hadoop ecosystem. In this lesson, I will show you with just 4 lines of Pig instructions how we can solve the same maximum closing price by stock symbol problem, which took a couple of pages of code with the Java MapReduce program. Before I go any further, I have to mention that this lesson just scratched the surface of Pig. Pig is a lot more involved and a highly powerful tool with a lot of features like complex data types, implicit casting, joining data sets, support for macros and functions, etc. What this lesson will give you for sure is a taste for this awesome tool. The files for this lesson is under hirw starter kit /pig/stocks. When you get into this directory, you'll see two files. maxcloseprice.pig is the file with pig instructions. And the README file has general instructions on how to run this pig script. So let's open the maxcloseprice.pig file. Take a look at the set of instructions. That is it. We can get the same result from these 4 lines of instructions as what we got with the MapReduce program. Pretty awesome, isn't it? So, pig instructions are written in pig Latin. What you see here is pig Latin instructions. Pig Latin is an easy to follow data flow language. Don't be scared that you have to learn a new language. It's not complicated at all. Let me walk you through step by step, okay? Take a look at the first instruction. Just read the instruction out loud. Load the dataset in location user hirw input stocks using pig storage comma as you're giving a list of columns like exchange symbol, date, open, high, low, close, volume, and adjacent close, and their corresponding data types. The load instruction is used to load the dataset. Since our dataset is a comma delimited dataset, we are using the pig storage load function. And you're also specifying the delimiter of your dataset, which is comma in our case. Then we give a list of columns with the corresponding data types to match with what we see in our dataset. That's simple, right? Finally, you give the loaded dataset a name. In our case, we are naming our dataset as stocks underscore record. In Pig, the stocks underscore record is called a relation. Each instruction will result in a relation. So stocks underscore record is a relation, group by symbol is a relation, maximum closing is a relation. You get the idea, right? So now we have the records loaded, and we have also given a name to the loaded records in the Pig script. So we can now use this name to refer to our loaded dataset throughout our Pig script. Remember, we are trying to calculate the maximum closing price by symbol. So the next thing we want to do is we want to group the records by symbol, and then we can calculate the maximum closing price by symbol. This instruction right here will group the records that you loaded by symbol. So we'll use the group by operator to group the records by symbol. Just read the instruction out loud. You're saying group stock underscore records, which is your dataset, by symbol. That is it. And give the resulting group by records a name. Here we are giving group by symbol as the name. Now that the records are grouped, we are ready to calculate the maximum closing price by symbol. Understanding the structure of group by symbol will help us understand the next for each instruction. Since group by symbol is a collection of stock records, group by symbol will result in 2 columns. The first column is the column which you use to group the records by. In our case, we use the symbol to group the stock records. So the first column in group by symbol will have symbol values like Apple, GE, Ford, etc. You get the idea, right? But how can we refer the first column in group by symbol? It's very simple. We can simply refer to the first column as group, like you're doing it here. So the symbol here corresponds to group. Next, the second column of group by symbol is a collection of stock records for a given stock symbol. Let's take this for example. The first record in group by symbol is a collection of stock records for the stock symbol Apple. So in this case, your first column value will be Apple, which can be referred by simply group. The second column value will be a collection of stock records because we are grouping the stock records by symbol, right? And you can refer to that collection as stock records, like this right here. Now let's look at the for each instruction. Read the for each instruction like this. For each record in group by symbol, give me the group, which is nothing but the symbol, and the maximum closing price from the collection of records. Since the records are grouped together, we need to refer to the close price as stock underscore records dot close. Make sense? Perfect. Finally, we can use the store operator to store the output into HDFS. And we are using the pick storage function to specify the delimiter. So in this case, our output will be symbol and the maximum closing price, which will be delimited by comma. And the output location is this output pick stocks in HDFS. That is it. The script is now ready. Now we are ready to execute this pig script in our cluster. But before we execute, let's talk about what will happen when we execute a pig script. Pig first analyze the entire pig script, optimize the script if possible, and convert the script or pig-laden instructions into one or more MapReduce jobs, and then submit the MapReduce jobs in the Hadoop cluster. So in the background, all the pig instructions will be translated into MapReduce job. But the nice thing is the user don't even have to know about the behind the scenes details. So let's try to execute the script in our cluster. You should have access to this cluster that I'm in right now, and you can execute the same script that I'm executing now. If you don't have access yet, get your free access at www.hadoopinrealworld.com/Hadoop starter kit. I've also included the URL in the lesson notes. So let's see how we can run this pig script. So if you go back to the directory, you can see another file called readme file. Open the readme file from the same directory. The readme file has instructions and details on how to execute the pig script. It has few information like what is the input location for the pig script, which we have already mentioned in the pig script, which is user HIRW input stocks, and where this pig script will produce the output, which is output pig stocks. The next is you want to delete the output directory first, because if the output directory is already there, pig will fail to execute. It will throw an error saying that the output directory is already there, so it cannot override the output directory. So the first thing to do is make sure to delete the output directory if it's already there. And then let's execute the pig script. So first let's delete the output directory. Okay, so the output directory is now deleted. Now it's time to execute the pig script. All you have to do is just say pig and give the script name. There you go. So now the pig is taking your instructions in and translating them into MapReduce jobs. So it has already started executing the MapReduce job in the Hadoop cluster. All along we can see the progress it is going to make. So it has already calculated it needs 4 splits, so it would launch 4 mappers. So there you go, the MapReduce job is now complete. Let's look at the output. So the output is stored in this location right here, output pig stocks. So we're going to say Hadoop fscat output pig stocks. Output pig stocks is a directory, so let's see what is in the directory and then let's try to output the file. Okay, so the output is stored in this file right here. So I'm going to say Hadoop fscat and give the file name. So there you go, here's your output. So a symbol with a closing price. That's exactly what we wanted. And this is the same output that we got from our MapReduce program. So there is no difference at all in the output, right? So finally, what I wanted to show you is, you can also see the MapReduce job, which was executed in our Hadoop cluster with this URL right here. So take this URL, open a browser, and copy the URL there. So there you go. This is our MapReduce job, which was executed by pig. As you can see here, the job name is pig-laden max close price.pig. So as you can see, there were 4 input splits as we saw. So we are seeing 4 mappers here, which was executed in different nodes. And then you can see we have 1 reduce. So the information that you see here is more similar to what we saw with our MapReduce job execution. Because it makes perfect sense, right? Because pig took your pig instructions and converted them into MapReduce job. But the beautiful thing here is we did not write a single line of Java code to produce the result, because pig behind the scenes took care of everything. That is it, guys. As I was saying, this is by no means a complete overview of pig. And there is a lot more cool stuff you can do, like joining multiple datasets, custom functions, etc. with pig. But I hope this lesson gave you a good introduction to Apache Pig. With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. Let me start this lesson with a question. Forget about Hadoop for a second. When you think of analyzing data, what immediately comes to your mind? For most of us, a database table would come to mind, right? It's not a surprise because we are so used to visualize the data in a table structure, in a row columnar fashion. And almost all of us are familiar with SQL. Data in Hadoop cluster is presented as files, and so far, MapReduce using a programming language or pig doesn't allow us to view the data in a table structure. So it is only logical to have a tool in the Hadoop ecosystem to represent the data sets in table structure and run SQL queries against it. Hive does exactly that. Hive was developed by Facebook and it is now a top-level Apache project. Just like Pig, it is also widely used in the industry. With Hive, you can create table structures for your dataset and then write SQL-like queries to analyze your dataset. That's every data analyst's dream, right? So Hive takes in a SQL query and converts the query into one or more MapReduce jobs and submit into the Hadoop cluster. So the question is, why do we need to have two tools, Pig and Hive, doing somewhat similar things? Pig takes in Pig instructions and convert into MapReduce. Hive take in SQL-like Hive queries and convert them into MapReduce, right? They're doing somewhat similar things. Pig and Hive were developed by Yahoo and Facebook respectively to solve the same problem around the same time. The capabilities of either tool was not fully transparent to both companies at the early stages of development, which resulted in the overlap. So the next question you might ask is, do companies use both Hive and Pig in the same cluster? The answer is yes. We have seen successful Hadoop implementation using both Pig and Hive in the same environment. Here is one such use case. You can use Pig for standard nightly ETL kind of jobs like extracting data, transforming and loading the data, doing some predefined aggregations. You can do that with Pig. And Hive can be used by developers, data analysts, and scientists on a day-to-day basis for ad hoc analysis of data. In this lesson, we're going to solve the same problem, that is finding the maximum closing price by stock symbol, but this time using Hive. And you'll see how easy and fun it is. This lesson doesn't mean to be a detailed overview of Hive, but will serve as a very good introduction to Hive. The scripts for this lesson is in this directory in our cluster, hirw starter kit /hive/stocks. You'll see a script with name maxcloseprice.q. So let's open the maxcloseprice file. So here's the script, right? So these are Hive queries. To work with Hive, you need to enter into Hive's shell. So let's type in Hive to get to the Hive shell. So now we are in Hive and we can execute Hive queries right in this prompt. The first step is to create a table in Hive. So let's go back to the other window. Here's the syntax for creating the table. If you have worked with any databases like MySQL or SQL Server, Oracle, etc., this syntax will be very familiar to you. You're creating a table with the name stocks_starter_kit and you're specifying the list of columns along with its data type. Also, you can see the data types you're seeing here for the Hive table looks very similar to the data types from Java. Our stocks dataset is a comma delimited dataset. So this line here indicates the column in the dataset is separated by comma. Row format delimited fields terminated by comma, which means this table is looking at a dataset which is comma delimited. The location attribute points to the location of the dataset in HDFS. So the dataset is in this location, user HRW input stocks. So let's execute this script to create the table. Go back to our Hive prompt, copy the script, there you go, the table is now created. Now we have created a table. Just like any table in a database, you can run SQL queries against this table. So let's try a simple select statement to bring in 100 records from this table. This table has a lot of records, so I don't want to print all the records on the screen. I just wanted to bring 100 records from this table. There you go. As a row, columnar structure, you're seeing the result set. This is perfect, right? This is not all the records in the data set. This is just 100 records from the data set. Now let's say someone else created this table and you want to get more information about this table, like the column information and the location of the data set, etc. You can use the describe formatted command to know more information about this table. So you're saying describe formatted and you're giving the table name. So let's try this command. As you can see, the first set of information from the describe formatted gives you the column names, the data type, etc. And it's also telling you who created the database, like who is the owner, and the location of the data set. That is, this table is pointing to a data set in this location right here. And the next important property is the table type, which in this case is external table. So if you go back to our create table script, you can see we have created the table as external table. What does it mean? There are two types of table in Hive, managed table and external table. With managed table, when you drop the table, the data in this location will be dropped or deleted. So you need to be very careful with managed tables. With external table, however, Hive does not delete the dataset when you drop the table. This is a preferred table type because since the same dataset can be shared by multiple applications like MapReduce, PicScripts, and Hive, you don't want to run into the risk of deleting the dataset accidentally by dropping the Hive table. So for that exact reason, we have made our table as an external table. You may also notice that we are using the same dataset in the same HDFS location for MapReduce program, Pig, and now Hive. So making the table external eliminate the risk of accidentally deleting the shared dataset when dropping this Hive table. Now we have the table ready and we can select the records from the table. It is now time to calculate the maximum closing price. So take a look at this query. It is a very simple SQL query. You're saying select symbol max close price from stocks underscore starter kit, which is our Hive table, and group the records by symbol. So this query is going to give you the exact output that we got from the MapReduce program and also from the Pig script. So let's try this query. So now Hive is taking this query, it is translating this query into a set of MapReduce jobs, and it's executing the MapReduce job into the cluster, just like what Pig did with Pig instructions. And you can also track this application by going into this URL. Here's the result set, the same exact result set that we got from a MapReduce program and from the Pig script, and the same exact result set. Just like you did with the MapReduce program or a Pig script, you can monitor the application with this URL. So let's copy this URL. There you go. Our Hive query is translated into this MapReduce job right here. As you can also see, the job name is populated by Hive, which is like select symbol max close price ... right? The state of the job is succeeded. So that is it. Beautiful, isn't it? Again, we just scratched the tip of the surface here for Hive. Hive provides a lot of interesting way to store your data with partitions, buckets, and also support powerful and more intelligent way of joining datasets. But I hope this lesson gave you a good introduction to Hive. With that, let's wrap this lesson. Hey guys, welcome back. I'm so excited to start a brand new chapter on Cloudera Manager. So far, when we did any installation or configuration, we did them manually. That is, step by step, and sure, it felt like a lot of steps. For example, when we converted our cluster to high availability cluster, it took time and it took several steps. Looking at all those steps, you probably were thinking to yourself, do I have to remember all those steps? What if I forget a small little detail? Don't worry, you're not alone. We all have the same doubts and we have all been there. Managing a cluster manually, node by node, especially in an environment like Hadoop, where you could potentially have thousands of nodes, is not entirely feasible. That is where administration tools come into play. Tools like Cloudera Manager make management and maintenance of Hadoop cluster painless. In the next series of lessons, you will see how easy it is to install Hadoop on a set of nodes, how easy it is to add and remove nodes to and from the cluster, how easy it is to add services like HDFS, Yarn, Flume, etc. You will see that all the tasks that we did manually can be done using Cloudera Manager with relative ease. I know what you're thinking. You're thinking, then why on earth did we went through so many lectures looking at manual installation, manual configuration, etc.? That is a fair and valid question. Tools like Cloudera Manager hide all the details and mask all the complexities of installation and configuration from the end user, which on the surface looks like a very good thing. But administrators who manage Hadoop cluster only through tools like Cloudera Manager lacks the understanding of what happens behind the scenes. For example, they don't know what configuration properties are involved in configuring Kerberos. What are the key tab files and what should be the permission of key tab files? Which files go where? They don't know any details about what's going on under the hood. And that is a big problem. When all things are going well, none of the under the hood details are necessary. But administrator job becomes stressful and highly visible only when there are issues, and without the under the hood details, he or she cannot effectively troubleshoot issues and solve real world problems. At Hadoop in Real World, we understand this, and that is why we focus on the hard details first and save the easy one for last. When we interview people for Hadoop administrator positions in our jobs, just in the first 5 to 10 minutes, by asking a couple of questions, we will easily find out whether a person knows what is going on behind the scenes. And if the person does not understand and know how to manually configure or install things, there is no way we will offer him a job. It breaks our heart when we see other Hadoop training places and Hadoop courses out there that cover only tools like Cloudera Manager without going into details. Those students are going to have a tough time when they manage Hadoop clusters in the real world. But you don't have to worry a bit because your foundation is very strong. All right, enough talking. Let's get down to business. In this lesson, we're going to look at the components of Cloudera Manager and the benefits of using Cloudera Manager. Sounds good? Let's get started. Before we look at Cloudera Manager's architecture, let's see what is Cloudera Manager capable of. Cloudera Manager is an end-to-end solution, starting from installation to monitoring and maintenance. Cloudera Manager supports click-by-click automated deployment and lets you stand up an enterprise-wide Hadoop cluster with ease. Next, Cloudera Manager helps administrator with end-to-end monitoring of the cluster. You can see the health of your services, health of individual nodes, information related to CPU, memory, etc. It also lets you configure alerts for critical events so you can proactively identify and troubleshoot issues. Next, Cloudera Manager allows administrators to manage Hadoop clusters with ease. You want to add a service, add or remove nodes to the cluster, or put a node or service in maintenance mode, all those tasks can be done with few clicks. So in summary, Cloudera Manager is an end-to-end solution to install, monitor, and maintain a Hadoop cluster. Cloudera Manager, as the name suggests, is a product from Cloudera, and it is licensed with Cloudera's enterprise license. And it lets you manage Cloudera's distribution of Hadoop. If you're using another Hadoop distribution, for example, Hortonworks, then you would use Apache Ambari to manage the cluster and not Cloudera Manager. Now to the architecture. Cloudera Manager is architectured in an agent-server model. Cloudera Manager runs as central server which hosts the application and the entire logic to manage Cloudera Hadoop clusters. Everything related to installing CDH, configuring services, starting and stopping services is managed by Cloudera Manager server. The Cloudera Manager agents are installed on every managed node. They are responsible for starting and stopping Linux process, unpacking configurations, triggering various installation paths, and monitoring that node. Agents are responsible for sending heartbeats about the services running on the node and the health of the node to the Cloudera Manager server. With the information provided by all the agents in the cluster, Cloudera Manager provides a consolidated view of all the services and nodes in the cluster. Next feature of Cloudera Manager is the one that administrators love. Cloudera Manager offers you two ways to install Hadoop and other components. One is through packages and the other way is through parcels. Packages are a traditional way of installing Hadoop and any other Hadoop components. So far in our course, anytime we install a component in our cluster, like name node or resource manager, we use package in our installation process. Let's refresh our memory a bit. Let's say we would like to install resource manager, we would say sudo apt get install Hadoop yarn resource manager. This command will download the resource manager component from Cloudera's website and begin installation. What version of Resource Manager will it download? Very simple. It will look up the file cloudera.list under etc apt sources list.d directory. Here in our cluster, we have specified the Cloudera version to be 5.1.2. So in our case here, Resource Manager version 5.1.2 will be downloaded and installation will continue. Now let's say we just installed Resource Manager version CDH 5.1.2 in our cluster. Later, let's say one of the administrators in your team went in and updated the cloudera.list file to 5.7. Now the same administrator is trying to install Node Manager. So when he issues a sudo apt get install Hadoop yarn Node Manager, the command will download and install Node Manager CDH version 5.7. Now you have components in your cluster with different versions. Your resource manager is running on version 5.1.2 and your node manager is running on 5.7, which is totally different. Even though it is highly unlikely an administrator going in and updating the version like that, but there is no one to validate the version conflicts during installation, and this will lead to a lot of issues. Now let's talk about parcels. Instead of having separate packages for each component in your Hadoop cluster, parcels have a single object for installation, self-containing all the components you would like to install. So the question is, what advantage does this provide? The very first advantage is version consistency between components. Since all the components are self-contained in a parcel, the version between components are validated for consistency and matched, eliminating version conflicts. And the next benefit is an interesting one. Traditionally, when you upgrade components to new version with packages, you would have to shut down the old process which is running. Then you will download package for the newer version of the component. Then upgrade the component, then start the component once the upgrade is complete. There are two problems with this approach. First, there is a significant downtime while you upgrade. And second, once the upgrade is complete and when you start the process, what if you experienced an error? You will spend a lot of time troubleshooting while the component is down. This increases the downtime of your Hadoop cluster, which is not ideal, correct? With parcels, you can stage the newer version of the component, meaning you can distribute a newer version of Hadoop components and leave it on the side without activating it while the Hadoop cluster still runs on the older version. When a new version is staged side by side, you can simply switch to a newer version by changing which version of CDH is used when restarting each process. You can then perform upgrades with rolling restarts, in which each component like name node, data node, resource manager, node manager, etc. are restarted in the correct order to switch to the newer version with minimal service interruption. You can perform stage installation with minor version upgrades. That is, if you're upgrading from CDH version 5.1.2 to 5.1.3. Major version upgrades, for example, CDH version 4 to CDH version 5 require a full service restarts and downtime because of substantial changes between the major versions. Next, with packages, Cloudera Manager only helps with the initial installation and subsequent version upgrades are left to you, and you need to perform it manually. Whereas with parcels, Cloudera Manager manages all the steps in the CDH version upgrade. With parcels, distribution and activation of the software are decoupled. As mentioned before with packages, when you upgrade, you stop the current component you're upgrading, run the installation to upgrade the component, and start the component which is upgraded. The operation is synchronous and happens one after the other. With parcels, all steps are decoupled. Now that's a good segue to talk about the life cycle of the parcels. Now let's say you're upgrading from version 5.1.2 to 5.1.3. You'll first download the new parcel version to Cloudera Manager server. And you would need internet connection for this, of course. Once downloaded, the second step is to distribute the parcels to all the other nodes in the cluster. Distribution simply unpacks the parcel on all nodes, and it will not affect any of the existing components, and all current components will still continue to run on the older version. To distribute the new parcel to individual nodes, you do not need internet connection because Cloudera Manager server and nodes are on your same internal network. You can have multiple parcels distributed on your clusters side by side at the same time. Remember, distribution does not mean that the new version is activated. Once distributed, you can activate the newer version at any time. You can technically wait months before activating the newer version once the newer version is distributed. Again, you can have different parcels for the same component at the same time running side by side, but you can decide which one to activate. Once the new parcel is activated, links to the parcels are created, and an administrator would restart the component or services that are upgraded. After the restart, the new parcel will be in use. To remove a parcel from the cluster, you would have to deactivate it first, and then you will remove the parcels from all the nodes in your cluster. Finally, you can choose to delete it. If you delete, it will delete the parcel from the Cloudera Manager server. This is the complete life cycle of parcels. That is it, guys. In this lesson, we talked about what is Cloudera Manager, the benefits of using a tool like Cloudera Manager. We also looked at the architecture of Cloudera Manager. And finally, we saw the benefits of using parcels versus using packages and the life cycle of parcels. In the next lesson, we'll stand up a Hadoop cluster using Cloudera Manager, and you will see how easy and fast it is. With that, let's wrap this lesson. See you in the next lesson. Hey guys, welcome back. In the last lesson, we saw the benefits of using Cloudera Manager, and we also saw the differences between packages and parcels. We saw the benefits of parcels and its advantages over packages. Given the benefits, we know parcels are the way to go. Finally, we finished the last lesson with looking at the life cycle of parcels. In this lesson, we're going to look at how to install a Hadoop cluster with Cloudera Manager. You will see how easy it is to install a cluster with Cloudera Manager as compared to installing and configuring a cluster manually. It will almost feel like cheating. I can hear you asking, then why did we not learn Cloudera Manager before? Why did we spend so much time learning to install and configure manually? I'm going to give you the same answer that I gave you in the last lesson. At Hadoop in Real World, we want our students to understand how things work internally. We love to teach our students shortcuts, tips and tricks, but more importantly, we'd love to get the foundation right. That is, knowing the under the hood or behind the scenes stuff. That is why we trained you with installing and configuring a cluster manually. All right, here's the game plan for this lesson. We're going to create 4 instances in AWS. We will use one instance to run Cloudera Manager server, and will install and configure Hadoop in the other 3 instances using Cloudera Manager. Let's first go to AWS and launch 4 instances. I'm in the home screen of AWS. Let's click on EC2 first. Now click Launch Instance. And here for the operating system, I'm going to choose Ubuntu Server 14.04. Select. Here for the instance type, I'm going to select T2 Medium, which comes with 4 GB RAM and 2 virtual CPU cores. Good enough for our demo. Next, let's move on to configuration details. Here, for the number of instances, I'm going to specify 4. And I don't make any more changes here on this screen. Let's move on to add storage. The default storage is set to 8 GB. I'm going to change that to 100 because 8 GB is too low. And for the volume type, I'm going to change it to magnetic from SSD because magnetic is cheap compared to SSD. Next, let's move on to tagging instances. I'm not going to tag the instances here. Let's move on to the next step. Here we have to select or create a new security group for our cluster for the nodes that we are creating. I'm not going to create a new one. Instead, I'm going to use an existing one. So I'm going to select an existing security group. Scroll down. I'm going to select this group, Cloudera Manager. Let me enlarge the screen here. As you know, security groups are set of rules which dictates which ports and protocols are allowed for these nodes to communicate with each other, and who can connect to the nodes, and on what port and protocol they can use to connect to these nodes. Here we have specified the specific port range and protocol that are allowed for connecting to these four instances. Take a look at this highlighted rule because it's very important. All nodes in Hadoop cluster should be able to talk and communicate with each other. So this rule specifies that all nodes using the Cloudera Manager security group can talk to each other on all protocol across all nodes. Without this rule in place, our nodes in the Hadoop cluster cannot talk to each other. So this rule here is very important. Let's go ahead, click on Next to review and launch. Here we get an alert saying that do we want to use SSD? I'm still going to stick with magnetic because magnetic is cheap, as I said, compared to SSD. So click on Next. And here's all the information about our four instances. Let's review it really quick. And let's go ahead and click Launch in a bit. For storage, let's make sure the size is 100 GB. Looks good. I'm going to say Launch. Here we have to select an existing key pair to log in to our instances. I'm going to select HARW because I have the key pair for HARW. The instances are now launching. Let's give a few more minutes and then let's go ahead and name our instances. I'm now back at the EC2 dashboard and now I see the new instances that we just created are in running status. So that's very good. So I'm going to name these instances as CMDemo1, CMDemo2, 3, and 4. So let's go ahead and name it CMDemo1, CMDemo2, CMDemo3, and finally CMDemo4. Now let's go ahead and note down the public and private DNS of these instances because we need them to refer them. So let's enlarge the screen here a little bit. Select CMDemo1 and here is the public DNS, here is the private DNS. So let's copy the public DNS first. There you go. Public DNS, private DNS. I'm going to do this quickly for the other three nodes as well. Now that we have saved the information for private DNS and the public DNS, let's go ahead and connect to CMDemo1. Because on CMDemo1 node, we're going to install Cloudera Manager and we're going to start the installation from that node. The other three nodes, that is CMDemo2, 3, and 4, is where we install all the Hadoop components. And those three nodes will become the three nodes of our Hadoop cluster. Make sense? All right. Let's go ahead and copy the public DNS of CMDemo1 and let's configure PuTTY to connect to that node. I'm going to put in the host name. For the save sessions, I'm going to say CMDemo1. Let's go to SSH. Select the private key. Go back to the session. I'm going to hit save. And I'm going to cancel from the PuTTY screen. I'm going to open mremote-ng. And this is the software that I use to connect to multiple instances side by side. So let's look for our CMDemo1. Here it is. All right. Type in Ubuntu. And there you go. Now we are logged into our newly created node. Let me clear the screen first. The next step is to download Cloudera Manager on this node and then start the installation using Cloudera Manager from this node. The latest version of Cloudera Manager at this time of installation is 5.7.1, which support installation for both CDH version 4 and CDH version 5 Hadoop cluster. And here is the URL to download the latest version of Cloudera Manager. So I'm going to issue a wget on this URL. So let's copy this URL. Go ahead and let's run it. And this URL is basically pointing to Cloudera's website. So we are downloading Cloudera Manager from Cloudera's website. So let's go ahead and run it. And here it is. The download is very quick. And let's go ahead and make sure the file is present. And there we see the file. Next step is to change the permission on this file so that I can execute the file. Just go ahead and copy these two commands and execute it. And there you go. Now we should have execute privileges on this file. Perfect. Now here's the command to start this executable. Here is the welcome screen for Cloudera Manager. Let's go on and say next. Again, here's the license for Cloudera Manager. I'm going to say next again. Do I accept the license? Of course, yes. And this is the Oracle binary code license. Of course, next. Accept the license again, yes. Now Cloudera Manager has begun its installation on this node. Let's wait for the installation to complete. It's going to take at least a couple of minutes. So let's come back once the installation is complete. Cloudera Manager is now installed on this node. Cloudera Manager has a very good user interface and it can be reached on port 7180 using admin as the user and admin as the default password. So that is exactly the information that you see here. Click OK. And there it is. Our installation was successful. Perfect. And here's the URL to reach the Cloudera Manager. We have to replace the public DNS name in this URL so that we can reach the URL. All right, so let's copy this URL, go to Firefox, run it, and here it is, the login screen for Cloudera Manager. For username, I'm going to say admin, and for password, I'm going to say admin as well. Hit login. The very first screen, of course, we're seeing the end user license terms and conditions. We're going to scroll over. We're going to accept the end user license. Click continue. When you install Cloudera Manager at your client location or in your company, you will already have a contract signed with Cloudera, so you will have full access to the enterprise version. Here, we have 2 months of free trial for Cloudera Enterprise, so I'm going to choose this. I'm going to say continue. Here on this screen, Cloudera Manager is listing all the services that are available as part of Cloudera Manager to begin your installation. So I'm going to say continue for this again. And here we have to specify all the hosts or nodes for our Hadoop cluster. So let's specify all 3 nodes as a comma separated list. That. Copy the next node. And also copy the final one. So let's hit search. And here you go. Cloudera Manager was able to recognize all our 3 nodes. So let's go ahead and hit continue. Now we have to choose the method of installation, that is packages versus parcel. From the last lesson, we know the differences between packages and parcels, and we know parcels are better and recommended. So we will choose parcels here. Next, we'll select the version of CDH. Of course, we're going to select the latest version of CDH, which is at this time of installation is 5.7.1. And we also get the options to choose additional parcels to include additional components for Kafka, Scoop, etc. We're not going to install Kafka and Scoop, so I'm going to say none. Now let's hit continue. And on the next screen, we have to provide the consent to install Oracle JDK on these 3 nodes. And also we'll choose to install Java Unlimited Strength encryption policy files because these files are needed if we later choose to enable Kerberos. So let's hit continue. This screen is important. Here we have an option to choose whether you want to use a single Linux user to run all services in Hadoop, or you would like to provide a user which has root privileges, and using that login, Cloudera Manager will create individual users for each services. For example, HDFS user will be used for HDFS service and Yarn user will be used to run and maintain Yarn service. You definitely want to have individual users for individual services. It is clean and manageable. So do not select single user here. So let's hit continue. Since in the last screen you did not select a single user, you have to give a user login that has root privileges. Here, let's specify the user on all these 3 nodes, which has root privileges. So I'm going to click another user. And Ubuntu has root permissions on all these 3 nodes. So I'm going to specify Ubuntu here. I'm going to say all hosts accept the same private key. So here I have to select the private key. So selecting the private key. And we don't have any passphrase, so I'm going to select continue. Ignore this alert. We're going to continue with no passphrase. Hit OK. And here it is. The cluster installation is in progress on all these 3 nodes. This is going to take few minutes, but at this point, Oracle JDK is being installed on all the 3 nodes. Now, if you remember from the last lesson, the Cloudera Manager agent will be installed on all the nodes that are running Hadoop services. So that is what is happening here. Cloudera Manager is now installing Cloudera Manager agent on all these 3 nodes. Now, the installation is completed on all 3 nodes. And just to clarify, we have only installed Oracle JDK and the Cloudera agent on these three nodes. We have not started our Hadoop cluster installation yet, so let's go ahead and click on Continue. We went over the parcels lifecycle in the last lesson, and here it is. Parcels are now being downloaded, distributed, unpacked, and activated. The parcel version that is being downloaded here is for CDH version 5.7.1, and the parcel version is 0.11. Now that the parcels are being downloaded, once the parcels are fully downloaded, we will see things will start to work parallelly. That is, as it is being distributed, unpacking will be in progress on the other nodes. This will take a few minutes. So let's give Cloudera Manager a few minutes. Now the packages are being distributed. And here at the bottom, you can see the actual status on the three nodes. You can see on the first and the second node, distributing is in progress, but on the third node, unpacking is in progress. And as you can see, things are being done parallelly across all three nodes. Now unpacking is in progress on the second node and also on the first node. Now here, parcels are being activated right now across all three nodes. Now the parcels are fully activated across all three nodes. Now let's go ahead and click on Continue. In the next screen, Cloudera Manager inspected all three nodes for correctness and looks like all the tests have been passed. So that is pretty good. So let's go ahead and click on Finish. Now it's time to install Hadoop components across all three nodes. Here, Cloudera Manager gives the option to specify the Hadoop services. We're going to just go with the core Hadoop services here, which will install HDFS, Yarn, Zookeeper, Oozie, Hive, and Hue. So I'm going to select core Hadoop. Click on Continue. The next step is to assign what services will be executed on each host. Cloudera Manager did some default assignments to our hosts, but we're going to make some slight adjustments. We're going to make this node as our primary node, that is 172.31.34.131 as our primary node, meaning we'll run the name node and the resource manager on this node. Usually in real production environments, the name node and the resource manager will not be executed on the same node. But since this is a demo, we'll make the name node and resource manager run on the same node for simplicity. So let's copy this. So let's click on the name node and select 31, hit OK. And for the data node, we're going to specify all hosts. And let's leave the secondary name node on 128, which is fine. Balance around 128, that is also fine. And for HTTPFS, let's select 28. Okay. NFS gateway, let's again select 28. Hive can be accessed from all three nodes, so we're going to leave as 128, 129, 31. And for web HCAT server, we're going to select 128. We're not going to use Hue for now, but let's run it on 128. Now for all the Cloudera management services, we're going to select the node 129 to run all Cloudera management services. So let's click on that. Click 129 for all the services. And don't worry, we're going to look at all these services in detail. So Oozie is fine. We're going to run the resource manager and job history server on 131. So let's switch to that. The node manager will be run across all nodes, that is same as data nodes. Zookeeper 128 is fine. Now that we have specified the role assignments for each of our hosts, let's click on Continue. Some of the services in our cluster, like Hive and Activity Monitor, would need to have access to a database. And for that, we're going to use the embedded database that comes with the Cloudera Manager. So let's use the embedded database. And we need to test the connection of the database. So let's scroll down, hit Test Connection. The test is successful. Let's click on Continue. Here are some of the important configuration details for our review. For example, the HDFS block size by default is chosen to be 128. Here is the local data node directory, and here is the local name node directory. We're going to leave the default configuration values as it is. So let's go ahead and hit Continue. Now, Cloudera Manager will take care of installation and starting each of the individual services. As you can see, the first step is to start the installation across all nodes for all the services that we have selected. Now, in the second step, Cloudera Manager is starting individual services. So let's give it a few more minutes for the installation and the starting process to complete. Right now, Cloudera Manager is starting HDFS. So far, everything looks good. HDFS is now started successfully. Next, Yarn is being started right now. Yarn is also successfully started. Next, we'll wait for 3 services to start, that is Hive, Oozie, and Hue, and then let's continue with the steps. Now all services have been successfully started. So let's go ahead and click on continue. And here's a congratulations screen. The services are installed, configured, and running on our cluster. So let's go ahead and hit finish. And there you go. Here's the home screen of Cloudera Manager once our cluster is fully started. We can see that we have all services installed and in good health. We'll go over each components and also the pages in Cloudera Manager in great detail in the upcoming lessons. But for now, we've successfully installed a 3-node Hadoop cluster in a matter of minutes using Cloudera Manager. Pretty cool, and it's easy, isn't it? Now that the installation is complete, why don't we go ahead and validate the installation? Let's go ahead and create a PuTTY session for this node for us to log in. So let's go ahead, open PuTTY. I'm going to name it CM Demo 2. Let's go select SSH auth, select the private key, go back to the session and save. Hit cancel here, open mremote ng, and then open CM Demo 2. Click yes, log in as Ubuntu. Now I'm logged into one of the hosts in our cluster. Before we go ahead with validating our Hadoop cluster, let's look at where the configuration files and installation directories are. First, the configuration files are under the same directory as before, that is cd etc hadoop conf. And here we see all the configuration files like HDFS site, core site, yarn site, map site.xml files that you're already familiar with. Now let's talk about the installation directory. If you're installing Hadoop with packages, you will see the installation files and folders under user lib in their respective directories. Since we did this installation using parcels, we will not see the installation files or folders under user lib. You'll find them under OPT Cloudera parcels directory. So let's go ahead and check this location. Let's clear the screen first. Let's say cd opt Cloudera parcels. Let's do a directory listing here. And here you can see the parcel directory. That is CDH 5.0.1 parcel 0.11. And the other listing is CDH, which is a link which points to the parcel directory. So now we know the configuration and the installation location. Let's go ahead and try out HDFS command and run a MapReduce program to validate the HDFS and yarn setup in our cluster. Before we try any HDFS command, let's go ahead and create an HDFS user directory for the user Ubuntu, because we are logged in as Ubuntu. So I'm going to run these 3 commands on HDFS. The first 2 commands is going to create 2 directories, user and Ubuntu, and the last command is going to change the permission on the user Ubuntu directory. So I'm going to copy these 3 commands. I'm going to run on this node. The first command failed saying user directory exists, so let's not worry about that. The second command created Ubuntu directory under the user directory, and the third command changed the ownership on the user Ubuntu directory. Now that we have created a user directory for Ubuntu, why don't we create a sample test file and upload the test file to user Ubuntu directory. So let's go ahead and create the test file. I'm going to name it as HDFS test. Let's say this is a test file. Save it. Now I'm going to say Hadoop FS copy from local. I'm going to say HDFS test to the directory user Ubuntu. The sample test file is now uploaded to the directory. Let's do a Hadoop FS ls. And there you go. The file is now uploaded to HDFS. So it looks like HDFS is now working perfectly fine. Now that we have verified HDFS, let's verify yarn. Let's run a MapReduce program that comes with the installation. Hadoop installation by default come with some MapReduce example programs, and one such program is PyEstimator. PyEstimator will estimate the value of pi using quasi-Monte Carlo method. The details of the program are not relevant here, but it can be used to validate the yarn installation and our whole MapReduce setup. You can find the PyEstimator in Hadoop example.jar under the directory opt Cloudera parcels cdh lib Hadoop 0.20 -MapReduce folder. The first parameter for the program is the number of mappers, and the second parameter is the number of samples per map. And here is the command to execute the program. Let's copy the command and let's execute it in our cluster. And there you go. The MapReduce program is now running. The map is now at 50%. The progress of the MapReduce program is good. Let's wait for the execution to complete. And there you go. The program is now complete, and here is the output. The estimated value of pi is 3.6000. Now we have successfully validated both HDFS and YARN. To summarize, in this lesson, we installed a brand new Hadoop cluster in a matter of minutes. We also looked at both installation and configuration folder locations. Finally, we validated HDFS and YARN. In the next lesson, we'll see how to actually work with Cloudera Manager, the terminologies used in Cloudera Manager, and the different pages and functionalities in Cloudera Manager. With that, let's wrap this lesson. See you in the next lesson. We are very happy and excited to announce that Hadoop in Real World course is live on udemy.com. You can go ahead and check out the course and its curriculum at udemy.com/Hadoop in Real World. This Hadoop in Real World course is designed for anyone who aspire a career as a Hadoop developer. In this course, we have covered all the concepts that every aspiring Hadoop developer must know to survive in real-world Hadoop environments. This course covers all the must-know topics like HDFS, MapReduce, YARN, Apache Pig, and Hive, etc. And we go deep in exploring the concepts. We just don't stop with the easy concepts. We take it a step further and cover important and complex topics like file formats, custom writables, input-output formats, troubleshooting, optimizations, etc. All topics are explained with the latest version of Hadoop. And all topics are backed by interesting projects like analyzing million-song dataset to find less familiar artists with hot songs, ranking pages with page dumps from Wikipedia, simulating mutual friends functionality in Facebook, just to name a few. We can certainly hope for a flawless execution of our Hadoop jobs in a Hadoop cluster, but that ain't going to be the reality all the time. When things don't work as planned, that is when you will feel the stress in your job, especially when your boss and your business users are expecting an ETA to fix the issues. So, we have exclusively covered topics like debugging, troubleshooting, and optimizations that you can practically apply on your day-to-day job. Plain text formats are cute, but knowing to work just with plain text files in Hadoop is just not going to cut it in a real Hadoop environment. We cover a variety of file formats in this course, like compressed files, sequence, and Avro files, to fully equip you with real-world file formats that are used in Hadoop. Learning to install Hadoop on a VM or a single node is like learning to swim by reading a book. We have a dedicated chapter with step-by-step walkthrough and install a 3-node Cloudera CDH 5.4 Hadoop distribution cluster on Amazon Web Services on EC2 instances. All softwares are prone to failures, and even our mighty Hadoop is no exception. Hadoop architecture has few single point of failures, and we should be fully aware of those. And most importantly, we need to know how to recover from those failures. Hence, for that reason, we have covered advanced architectural concepts in this course. We have even lessons to cover how you should prepare for Hadoop interviews. And wherever possible, we have included difficult questions that are asked in real Hadoop interviews in our lessons. This will help you prepare yourself well for Hadoop interviews as you go through the course. Here are a few reasons why we feel Hadoop in Real World course is a lot different from other courses out there. Most courses are shallow and cover just the basic concepts without fully exploring the power of Hadoop. We cover all the concepts that we feel necessary in a Hadoop job, ranging from writing custom input-output formats, working with different custom file formats like Avro files, to performing optimizations to your code. We go deep in our explanations to help you understand the concepts like no other courses out there. The example or projects from other courses are just simply boring and lack imagination. Projects in Hadoop in Real World course include analyzing million-song dataset, page ranking, simulating common friends problem in Facebook, just to name a few. Each project is handpicked to be interesting and also to illustrate a unique concept. When you sign up for the course, you will get a personal account to access a real Hadoop cluster. This will help you try what you learned right away without wasting a lot of your precious time in fiddling with virtual images. Supporting our students is our top priority, and we take great pride in providing quality and fast response to our students' questions and concerns. Not a lot of courses can claim that. Check out our responses to our students' question in Hadoop Starter Kit course, which is a free introductory course on Hadoop from us at udemy.com. We have included bonus lessons in our course to help you prepare for interviews. When you sign up for the course, you get two bonuses. The first bonus will help you while you learn Hadoop, and the second bonus will help you once you complete the course. Bonus number 1. How you can learn to play a guitar without a guitar, right? Similarly, when you learn Hadoop, you need to practice on a real multi-node cluster. Learning Hadoop with a packaged virtual image is like learning to play a guitar with a violin. It's just not the same. When you sign up for this course, you will get a personal account to access a real 3-node Hadoop cluster hosted on Amazon Cloud. Bonus number 2. Hadoop Developer Interview Guide is an excellent interview guide from BigDataInterviewQuestions.com, which has over 100 interview questions that were asked in real Hadoop interviews. When you sign up for this course, we'll give you a 50% discount for the guide. Even better, sign up for the course and write us a honest review, and we'll give you the guide for free. In addition to the free cluster access and an opportunity to get the Hadoop Developer Interview Guide for free, all our Hadoop Starter Kit students get a $50 discount to the course. The original price of the course is $200, and as a Hadoop Starter Kit student, you can get the course for $150 using the coupon code StarterKit50. You can either click the URL linked to this lesson to get the discount, or if you're on udemy.com, simply search for the course Hadoop in Real World and redeem the coupon code StarterKit to get the $50 discount. We have also included 3 more videos in the resources section of this lesson to explain more about the course. The first video elaborates on the challenges that are faced by Hadoop developers in their day-to-day jobs, and how Hadoop in Real World course address those challenges. Next video describes the hands-on interesting projects that we will cover in the Hadoop in Real World course. And the final video goes into detail of how Hadoop in Real World course is a lot different from all other courses out there. Don't miss to check those videos. So if you are ready to learn Hadoop the right way, sign up with the Hadoop in Real World course and we will make you an expert Hadoop developer. Thank you so much for watching.